Picture yourself standing alone on a vast, windswept plain. The ground beneath your feet stretches out in every direction, a seemingly endless expanse of earth and grass, unbroken by hills or trees. You turn slowly, taking in the world around you, and your eyes settle on the horizon. It's a perfect, unwavering line, sharp and straight, as if someone took a ruler and drew it across the edge of existence. The sky above is a deep, twilight blue, and the horizon seems to hold it in place, like the seam of a cosmic tapestry. Now let your mind linger on this moment. Why does the horizon feel so flat? Why does it look like the Earth itself is a giant, unyielding canvas stretching infinitely outward? This simple observation, this flat, unchanging horizon, is where our journey begins. For centuries, perhaps millennia, humans have gazed at the horizon and wondered about the shape of the world. In our modern age, science tells us the Earth is a globe, a spinning sphere hurtling through space, its surface curved ever so slightly. Yet, when you stand on that plain, or perhaps at the edge of a calm sea, the horizon betrays no hint of this curvature. It's flat, resolute, almost defiant. This paradox, this enigma of the flat horizon, has sparked curiosity, debate, and even obsession. Some see it as evidence of a flat Earth, a world not spherical but planar, a disk or a plane under a domed sky. Others see it as a trick of perception, a quirk of our limited senses. In this opening segment, we're not here to argue for or against a flat Earth. Instead, we'll use this mystery as a lens, a way to explore the boundaries of perception, the nature of belief, and the fragile line between what we see and what we know. So, take a slow, deep breath, and let's step into the enigma of the flat horizon, a question that feels as old as the Earth itself. Imagine you're a sailor, centuries ago, standing on the deck of a wooden ship as it glides across a glassy sea. The horizon is your guide, your constant companion. It's always there, always flat, no matter how far you sail. You might wonder, if the Earth is round, shouldn't the horizon curve? Shouldn't it dip or bend, revealing the planet's shape? This question isn't just a modern curiosity. It's one that has haunted thinkers, explorers, and dreamers throughout history. It's a question that feels personal, almost intimate, because it's rooted in what you see with your own eyes. And what you see is a flat horizon, a line that seems to whisper, the world is not what they say it is. Let's dive deeper into this mystery, peeling back the layers of perception, science, and philosophy to understand why the horizon captivates us, why it feels so deceptive, and what it reveals about our place in the cosmos. The flat horizon is, at its core, one of the most intuitive and compelling arguments for a flat Earth. When you stand on a beach, gazing out at the ocean, or in a desert, where the land stretches unbroken to the edge of your vision, the horizon presents itself as a straight, horizontal line. There's no curve, no arc, no hint of the spherical Earth that science describes. Flat Earth proponents often point to this observation as a kind of unassailable truth. Look for yourself, they say. Your eyes don't lie. If the Earth were a globe, you'd see the curvature. You'd see the world bending away from you. It's a powerful argument, not because it's scientifically correct, but because it's grounded in direct experience. Our senses are our first window into reality, and when those senses tell us the horizon is flat, it's hard to dismiss them outright. To understand why the horizon appears flat, we need to step into the realm of science, but let's do so gently, as if we're unraveling a story. The Earth, as we know from countless measurements, photographs, and calculations, is a globe with a circumference of roughly 40,000 kilometers. That's an enormous distance, so vast that the curve of the Earth is subtle, almost imperceptible to the naked eye at ground level. Imagine the Earth as a giant beach ball, but one so massive that you're standing on a tiny patch of its surface. If you look out across that surface, the curve is so gradual that it blends into a straight line from your perspective. The horizon, in scientific terms, is the point where your line of sight becomes tangent to the Earth's surface. the farthest point you can see before the planet's curve drops away. But because the Earth is so large, that drop is minuscule, too small to notice without specialized tools or a higher vantage point. Let's paint a picture to make this clearer. Imagine you're standing on a perfectly smooth, flat table that stretches out for miles. If you look to the edge of the table, you'd see a sharp, straight line where the table ends. Now, imagine that table is actually the surface of a giant sphere, so large that you can't perceive its curve. From your low vantage point, the sphere's surface still looks flat, and the horizon, the edge of what you can see, appears as a straight line. This is what's happening when you gaze at the Earth's horizon. The curvature exists, but it's so subtle that it's effectively invisible to the human eye at ground level. To see the curve, you need to rise higher, say to the altitude of a weather balloon or an airplane. At 35,000 feet, pilots can sometimes glimpse the gentle arc of the Earth, and from space, astronauts see the planet's unmistakable roundness. But down here on the ground, the horizon plays a trick on us, presenting a flat line that feels like a challenge to everything we've been taught. This phenomenon isn't just a quirk of geometry. It's also a product of how our brains process visual information. Our eyes and minds are wired to interpret the world in ways that are practical for survival. A flat horizon is simpler to navigate than a curved one. Our ancestors didn't need to account for the Earth's curvature when hunting, farming, or building shelters. So, our perception evolved to prioritize what's immediate and useful, not what's cosmically accurate. This is why the flat horizon feels so intuitive, so right. It aligns with our everyday experience, even if it contradicts the broader reality. Historically, the flat horizon shaped how early civilizations understood the world. Ancient cultures like the Mesopotamians, Egyptians, and early Hebrews often envisioned the Earth as a flat disk, sometimes covered by a dome-like sky. The horizon was the boundary of their world, a physical and metaphysical edge where land met sky. In Mesopotamian cosmology, the Earth was a flat plane floating on a cosmic ocean, with mountains anchoring it in place. The horizon's flatness reinforced this view. It was a visual confirmation of a finite, contained world. It wasn't until Greek philosophers like Pythagoras, around the 6th century BCE, began to propose a spherical Earth that this perspective shifted. Pythagoras and later thinkers like Aristotle noticed patterns that a flat Earth couldn't explain. The curved shadow during lunar eclipses, the changing positions of stars as one traveled north or south, and the way ships disappeared bottom first as they sailed away, as if sinking into the curve of the Earth. These observations laid the groundwork for a spherical model, but they required people to trust abstract reasoning over their own eyes. The flat horizon's persistence in flat Earth arguments today is a kind of echo of those ancient worldviews, amplified by modern skepticism. Proponents often challenge the scientific narrative by emphasizing direct observation. Go to the beach, they might say. Look at the horizon. It's flat. No curve, no globe. They may even use tools like lasers or telescopes to argue that distant objects, which should be hidden by the Earth's curve, remain visible, suggesting a flat plane. Science counters these claims with precise measurements. Surveyors, for example, account for the Earth's curvature when mapping large distances, and GPS systems rely on a spherical model to function accurately. Yet, the flat horizon remains a cornerstone of flat Earth rhetoric because it's so visceral, so immediate. It's not just an observation. It's a feeling, a conviction that what you see must be the truth. To deepen our understanding, let's consider an analogy. Imagine you're an ant crawling across the surface of a basketball. To you, the basketball surface seems flat because the curve is so gradual relative to your tiny size. The horizon, the farthest point you can see, looks like a straight line, even though you're on a sphere. Now, scale that basketball up to the size of the Earth, and you're in the same position as a human standing on the ground. The curve is there, but it's too vast to perceive without stepping back or climbing higher. This analogy helps explain why the horizon deceives us, but it also raises a question. If our perspective is so limited, how do we know what's true? This is where the flat horizon becomes more than a visual phenomenon. It becomes a gateway to philosophical and existential inquiry, a puzzle that invites us to question the very nature of reality. The enigma of the flat horizon is more than a curiosity about geometry or optics. It's a profound challenge to how we know what we know. At its heart lies a question that has echoed through philosophy for centuries. Can we trust our senses to reveal the truth about reality? When you stand on that windswept plain or at the edge of the sea, the horizon tells you one thing: the Earth is flat. But science, with its measurements, equations, and images from space, tells you another. The Earth is a globe. This tension between what you see and what you're told touches on the field of epistemology, the study of knowledge, and how we acquire it. The flat horizon asks us to weigh direct observation against abstract evidence, intuition against reason, and it's not always an easy balance to strike. Let's linger on this tension for a moment. Imagine you're a child, seeing the horizon for the first time. You point to that flat, distant line and ask, why does it look like that? An adult might say, the Earth is round, but it's so big you can't see the curve. As a child, you might nod, but part of you wonders, if the Earth is round, why doesn't it look round? That childlike curiosity, that instinct to trust your eyes, is what makes the flat horizon so compelling. It's not just a visual trick. It's a reminder that our senses are our first guide to the world, and when they conflict with what we're taught, it can feel like a betrayal. The flat horizon challenges us to question not just the shape of the Earth, but the reliability of our own perception. If something as fundamental as the planet's shape can feel so deceptive, what else might we be misinterpreting? What other truths might be hiding behind the veil of appearances? This paradox invites us to explore the limits of human observation. Our senses are powerful, but they're also finite. Our eyes can't see infrared light or detect the Earth's magnetic field. Our ears can't hear the low-frequency rumbles of distant earthquakes. Our brains, remarkable as they are, evolved to prioritize survival over cosmic accuracy. The flat horizon is a humbling reminder of these limitations. It's unsettling to think our eyes might betray us, to realize that what feels like an unshakable truth, the flatness of the world, might be an illusion. Yet, there's a strange comfort in this realization, too. It means our minds are capable of transcending appearances, of seeking answers beyond what's immediately visible. Through reason, experimentation, and imagination, we can uncover truths that our senses alone can't reveal. The flat horizon also raises questions about belief and authority. In the context of flat Earth theories, the horizon is often framed as a kind of rebellion against mainstream science. Proponents argue that the scientific establishment, NASA, universities, governments, has constructed a narrative of a spherical Earth that contradicts common sense. The flat horizon becomes a rallying cry, a call to trust your own eyes over the pronouncements of experts. This perspective resonates in an age of skepticism, where distrust in institutions is widespread. The horizon's flatness feels like a secret kept in plain sight, a truth that anyone can verify just by looking. But this raises a deeper question. How do we decide what to believe when our senses and our sources conflict? Do we trust the sailor's eyes, the scientist's calculations, or something in between? To explore this further, let's consider a historical parallel. In the 16th century, when Copernicus proposed that the Earth orbits the Sun, he faced resistance not just from the Church, but from common sense. The Earth feels stationary. When you stand still, you don't sense the planet spinning at 1,600 kilometers per hour or hurtling around the Sun at 107,000 kilometers per hour. The flat horizon, similarly, feels like evidence of a static, planar world. Copernicus's heliocentric model required people to trust abstract mathematics and observations, like the retrograde motion of planets, over their immediate experience. The flat horizon, in a way, is a modern echo of that struggle. It asks us to grapple with the same tension, the pull of intuition versus the weight of evidence. This tension isn't just intellectual, it's existential. The flat horizon invites us to question our place in the cosmos. If the Earth is a globe, we're inhabitants of a tiny, spinning planet in an incomprehensibly vast universe. If the Earth were flat, as some imagine, it might feel more like a stage, a contained world designed with purpose and meaning. The flat horizon, with its deceptive simplicity, whispers of a cosmos that's closer, more knowable, more centered on us. There's a comfort in that vision, a sense of being at the heart of creation. But there's also an unease in realizing that comfort might come at the cost of truth. What does it mean to live in a world where appearances and reality diverge? What does it mean to seek truth when our senses, our first allies, might lead us astray? Let's pause here as the video's soothing tone encourages reflection. Close your eyes for a moment if you like and picture the horizon you last saw. Maybe it was the edge of a lake, a mountain range, or an urban skyline softened by distance. What did it make you feel? Did it feel like the end of the world or the beginning of something vast? When you look at the horizon, what do you really see? Not just with your eyes, but with your mind. This moment of stillness, this gentle invitation to reflect, is part of what makes this journey so meditative. The flat horizon isn't just a puzzle to solve. It's a mirror, reflecting our curiosity, our doubts, and our desire to understand. The implications of the flat horizon extend beyond science and philosophy into the realm of human experience. It's a reminder that we're creatures of both instinct and intellect, forever balancing what we feel with what we know. It's a call to humility, to recognize that our perspective is just one angle on a vast, multifaceted reality. And it's an invitation to wonder, to let the mysteries of the world, like the flat horizon, spark questions that linger in the quiet moments before sleep. As you listen to this, perhaps lying in bed with the lights dimmed, let the enigma of the flat horizon settle into your thoughts. It's not about finding a final answer. God knows what shape the earth is, but it's about exploring the boundaries of what we perceive and what we believe. As we linger on the deceptive flatness of the horizon, our minds filled with questions about sight, truth, and the shape of our world, let's shift our gaze from the earth to the heavens. The horizon may hold secrets, but what do the stars and celestial bodies above us reveal about the earth's form? If the horizon appears flat, how do the movements of the sun, moon, and stars align with that vision? Let's drift upward into the quiet expanse of the night sky and explore a celestial mystery that flat earth theories often invoke, a mystery that promises to deepen our journey into the unknown. Close your eyes for a moment and imagine a clear, moonless night. You're lying on a soft blanket in an open field, far from the glow of city lights. Above you, the sky unfurls like a vast, velvet curtain, speckled with countless stars that shimmer and pulse. As you gaze upward, the heavens seem to curve gently, arching over you like a glittering dome, a celestial canopy that feels both infinite and intimate. The stars appear to wheel slowly around a fixed point. The North Star, steadfast and unmoving, creating the illusion of a contained, enclosed cosmos. This vision, this sense of a sky that embraces the earth, is at the heart of the celestial dome, a concept central to flat earth cosmology. Flat earth enthusiasts describe the sky not as an endless expanse of space, but as a physical firmament, a solid or translucent dome encasing a flat plane with the sun, moon, and stars as lights or projections on its surface. This idea is poetic, almost biblical in its resonance, evoking ancient myths of a world sheltered by a divine canopy. It feels like a story whispered by our ancestors, a tale of a cosmos that's close, purposeful, and knowable. But why does this vision of a celestial dome persist in modern imaginations, even in an age of telescopes, spacecraft, and cosmic discovery? Why does the night sky, with its arching stars, feel like a dome rather than a boundless universe? In this segment, we'll unravel the mystery of the celestial dome, not to affirm or debunk it, but to explore its allure. We'll journey through the interplay of perception and reality, the clash of ancient belief and modern science, and the human longing for a cosmos that feels like home. So, settle into this moment, let your breath slow, and let's drift into the illusion of the celestial dome, a mystery that invites us to question the very shape of the heavens. Picture yourself as a nomadic storyteller thousands of years ago, sitting by a crackling fire under a star-filled sky. Your tribe gathers around, their faces illuminated by flickering flames, as you point to the heavens and describe the world. You tell them the sky is a great dome, a protective shield crafted by the gods, holding the stars like jewels in its embrace. The sun and moon, you say, are divine lanterns, circling above the flat earth to bring day and night. Your listeners nod, their eyes tracing the arc of the sky, and the story feels true because it matches what they see. This ancient vision, rooted in observation and imagination, is the foundation of the celestial dome. It's a concept that has captivated humanity across cultures and eras, from the firmament of Genesis to the cosmic vaults of Mesopotamian lore. As we explore this idea, we'll ask, what makes the dome so compelling? How does it shape our understanding of the cosmos? And what does it reveal about our place beneath the stars? The celestial dome is a cornerstone of flat Earth cosmology, a model that imagines the sky as a tangible, dome-like structure arching over a flat, planar Earth. In this view, the stars, sun, and moon are not distant celestial bodies, stars burning billions of kilometers away, or a moon orbiting a spherical planet, but rather lights or projections embedded in or moving across the inner surface of this dome. The dome, often called the firmament, is seen as a physical barrier, sometimes solid, sometimes translucent, that separates the Earth from whatever lies beyond, perhaps a divine realm, an unknown void, or nothing at all. This concept stands in stark contrast to the scientific understanding of the cosmos, a vast, three-dimensional universe where the Earth is a spherical planet, roughly 12,742 kilometers in diameter, rotating on its axis and orbiting a sun 149.6 million kilometers away, within a galaxy among billions in an expanding universe. The allure of the celestial dome begins with observation. On any clear night, the sky does indeed appear to curve above us, like a great bowl inverted over the Earth. The stars seem to rotate in a predictable pattern, circling around the North Star, Polaris, in the northern hemisphere, creating the impression of a fixed, enclosed system. To someone standing on the ground, without telescopes or spacecraft, this motion feels like the sky itself is turning, as if the stars are affixed to a rotating dome. Flat Earth proponents seize on this perception, arguing that the sky's apparent structure is evidence of a literal firmament. They point to the North Star's steadfast position, the consistent paths of constellations, and the way the heavens seem to close around the Earth, suggesting a contained, purposeful design. Some even propose that the dome is a physical barrier, preventing humans from reaching the stars, or that the lights we see are projections, like a cosmic planetarium. To understand why the sky feels like a dome, let's turn to science, but let's do so gently, as if we're stargazing with a friend. The Earth rotates on its axis once every 24 hours, spinning from west to east at a speed of about 1,600 kilometers per hour at the equator. This rotation causes the stars to appear to move across the sky, rising in the east and setting in the west, while the North Star remains nearly stationary because it lies almost directly above the Earth's rotational axis. From our perspective, this motion creates the illusion of a rotating celestial sphere, a concept astronomers have used for centuries to map the stars. The dome effect is further enhanced by the way our eyes perceive the sky. Because we can't judge the distance to the stars, they appear to lie on a curved surface at a uniform distance, like lights on a planetarium ceiling. This is a trick of perspective, not unlike how parallel railroad tracks seem to converge in the distance. The sky isn't a dome, but our brains interpret it as one because it's a simpler way to process the vastness above. Let's explore this with an analogy. Imagine you're inside a planetarium, a darkened room with a curved ceiling. A projector casts thousands of tiny lights onto the ceiling, mimicking the stars. As the projector rotates, the lights move in unison, creating the illusion of a starry sky turning above you. In a flat Earth model, the celestial dome is like that planetarium ceiling, a physical surface holding the stars, sun, and moon, which move or are projected to create the patterns we observe. The scientific view, however, is more like stepping outside the planetarium into the open air, where the stars are not on a ceiling but scattered across unimaginable distances, their apparent motion caused by the Earth's rotation. The planetarium analogy captures the heart of the celestial dome's appeal. It's intuitive, contained, and comforting, transforming the chaotic vastness of the universe into something tangible and familiar. Historically, the idea of a celestial dome is deeply rooted in human culture. In the Hebrew Bible, the book of Genesis describes a firmament created by God to separate the waters above from the waters below, a solid vault holding the heavens. The Hebrew word for firmament, rakia, suggests something beaten out or spread, like a metal sheet or canopy. This vision influenced early Judeo-Christian cosmology, where the earth was a flat plane under a domed sky, with the sun, moon, and stars as divine lights. Similarly, ancient Mesopotamians imagined a flat earth covered by a cosmic vault, while Egyptian mythology depicted the sky goddess Nut arching over the earth, her body studded with stars. These cosmologies weren't scientific in the modern sense, but they were profound attempts to make sense of the world, blending observation, mythology, and spirituality. The Greek philosopher Aristotle, in the 4th century BCE, proposed a spherical Earth within a series of concentric celestial spheres, a model that retained the idea of a structured cosmos, but aligned with emerging evidence of the Earth's shape. Over time, the dome gave way to a more expansive view, solidified by Copernicus, Galileo, and modern astronomy, which revealed a universe of staggering scale. Yet, the celestial dome persists in flat Earth theories because it resonates with our senses and emotions. Proponents often cite ancient texts, like Genesis, or point to the sky's apparent rotation as evidence of a firmament. They may argue that the North Star's fixed position, or the fact that certain constellations are visible only in specific hemispheres, supports a dome-like structure rather than a spherical Earth in a vast universe. Science counters these claims with precision. The North Star's position is explained by the Earth's axial tilt, and the visibility of constellations depends on one's latitude because the Earth's curvature blocks parts of the sky. Telescopes reveal stars as distant suns, not projections, and spacecraft have ventured beyond the atmosphere, finding no dome. Still, the dome's appeal lies in its simplicity. It offers a cosmos that's finite, purposeful, and centered on humanity, a stark contrast to the scientific universe, which can feel cold and indifferent. To deepen our understanding, consider another analogy. Imagine you're a child spinning in a field, arms outstretched, watching the world blur around you. The sky seems to spin above, the stars tracing circles, as if the heavens themselves are turning. In that moment, it's easy to believe the sky is a dome, and you're at the center of it all. Flat Earth cosmology captures that childlike intuition, that sense of being at the heart of a cosmic dance. But science invites you to stop spinning and look closer. The motion is yours, not the sky's. The Earth's rotation creates the illusion, and the stars are far more distant than they seem. This interplay of perception and reality is what makes the celestial dome so fascinating. It's a reminder that what we see is only part of the story. The celestial dome is more than a quirk of perception or a relic of ancient cosmology. It's a profound challenge to how we construct our understanding of the cosmos. At its core, it asks us to consider a deceptively simple question. If the sky feels like a dome, does that make the scientific model of an infinite universe less intuitive? When you lie under the stars, the heavens seem close, almost touchable, as if you could reach up and pluck a star from the sky. The dome illusion taps into this instinct, offering a cosmos that's contained, protective, and purposeful. In contrast, the scientific universe, with its billions of galaxies, each containing billions of stars, stretching across 93 billion light-years, can feel overwhelming, even alienating. The celestial dome, then, isn't just about the shape of the sky. It's about the human need for boundaries, both physical and metaphysical. Let's linger on this idea of boundaries. A dome feels like a shield, a barrier between us and the unknown. It suggests a world designed with intention, where the stars are placed for our benefit, like lanterns hung by a cosmic caretaker. This vision is deeply comforting, especially in moments of existential doubt. When you gaze at the night sky, it's easy to feel small, insignificant, a fleeting speck in an incomprehensible void. The celestial dome counters that dread with a sense of enclosure, a cosmos that's finite and knowable, where humanity holds a central place. But this comfort comes with a cost. It requires us to set aside the evidence of telescopes, satellites, and mathematical models that reveal a universe far vaster than any dome could contain. The tension between these visions, between the dome's intimacy and the universe's immensity, raises a profound question. What does it mean to live in a cosmos that might be too vast to comprehend? This question touches on the field of philosophy, particularly metaphysics, which explores the nature of reality. The celestial dome challenges us to examine how we balance intuition and evidence in our quest for truth. The sky looks like a dome, and for much of human history, that was enough to shape our beliefs. Ancient cultures didn't have telescopes or spacecraft, but they had eyes, stories, and a need to make sense of the world. Their cosmologies, with their domes and firmaments, were not failures of reason, but triumphs of imagination, ways to navigate the mystery of existence. Today, science offers a different path, one grounded in observation, experimentation, and mathematics. Yet, the dome's persistence in flat Earth theories suggests that intuition still holds sway, that the human heart craves a cosmos that feels like home. The celestial dome also raises questions about purpose and design. In flat Earth models, the dome is often seen as evidence of a created world, a stage set for human life. The stars, sun, and moon are not random phenomena, but deliberate fixtures, placed to guide, illuminate, or inspire. This idea resonates with spiritual and religious traditions that view the cosmos as a reflection of divine order. In contrast, the scientific universe is indifferent, governed by physical laws that operate without regard for human significance. The dome's appeal lies in its promise of meaning, a cosmos where we're not just accidents of chemistry, but central actors in a grand narrative. But this promise comes with a challenge. If the dome is an illusion, what does that say about our search for purpose? Are we projecting our desires onto the sky, seeing a dome because we need to feel sheltered? Let's explore this through a historical lens. In the Middle Ages, European scholars built on Aristotle's celestial spheres, imagining a cosmos of nested, transparent spheres carrying the planets and stars around stationary Earth. This model was both scientific and theological, aligning with the Church's view of a God-centered universe. When Copernicus proposed a heliocentric model in the 16th century, placing the sun at the center, it wasn't just a scientific revolution. It was a philosophical upheaval. The Earth was no longer the cosmic hub, and the celestial spheres gave way to an open, infinite space. The celestial dome, in its modern flat Earth form, is a kind of rebellion against that shift, a return to a cosmos that feels personal and contained. It's a reminder that scientific progress often challenges our deepest intuitions, forcing us to rethink our place in the universe. This tension between intuition and evidence extends to the human psyche. The celestial dome resonates because it mirrors our emotional need for boundaries. Psychologically, we seek closure, certainty, and a sense of belonging. An infinite universe, with its vast distances and impersonal laws, can evoke existential dread, a fear of being lost in a cosmos that doesn't care. The dome counters this by offering a finite, enclosed world, where the stars are close enough to touch, and the sky feels like a protector. But this raises an unsettling question. Are we drawn to the dome because it's true, or because it soothes our fears. Are we seeing the sky as it is, or as we wish it to be? Let's pause here, as the video's meditative tone invites reflection. If you're listening in a quiet room, perhaps with the light's dim incarnation of the dome, its stars, its sun, its moon, feels like a story told to comfort, to make the vastness bearable. As you drift towards sleep, let the image of the celestial dome linger in your mind, a shimmering canopy above a quiet world. As we rest beneath the illusion of the celestial dome, our thoughts swirling with questions about the sky and our place beneath it, let's shift our focus from the heavens to the earth below. If the sky is a dome, what forces hold us to the ground? If the earth is flat, how do flat earth models explain the pull we feel, the weight that anchors us? Let's dive into a paradox that defies our everyday experience, a mystery that challenges the very ground beneath our feet. Take a moment to feel the ground beneath you. Whether you're lying in bed, sitting on a chair, or standing on a quiet floor, there's a subtle, constant force holding you in place. It's so familiar, so ever-present, that you rarely notice it until you drop something. A pen slips from your hand, and it falls to the floor with a soft clatter. A glass tips over, and water spills downward, not sideways or upward, but always toward the earth. This invisible pull, this gentle tug that keeps us anchored, is what we call gravity. It's a force that shapes our every moment, from the way we walk to the way rivers flow and rain descends from the sky. But what if gravity, as we understand it, isn't real? What if the Earth isn't a spinning globe exerting a force toward its core, but a flat plane with an entirely different mechanism to explain why things fall? This is the gravity defiance paradox, a cornerstone of flat Earth cosmology that challenges one of the most fundamental concepts in science. Flat Earth theories often reject gravity as we know it, proposing alternative explanations: density, buoyancy, or even the bizarre idea that the Earth is accelerating upward through space. How can a flat plane mimic the pull we feel on a spherical planet? How can something as intuitive as the fall of a pen be explained without the force we've been taught to trust? This paradox is not just a scientific puzzle. It's a philosophical challenge, a question that invites us to rethink the invisible forces that shape our reality. As we embark on this exploration, imagine yourself as a curious wanderer, standing on the edge of a vast, flat plain, feeling the earth beneath you and wondering, what truly keeps me grounded? Let's dive into this enigma with a calm, open mind and unravel the mystery of the gravity defiance paradox, a concept that feels both unsettling and strangely liberating. Picture yourself as a medieval alchemist, hunched over a cluttered table in a candlelit room, pondering the nature of the world. You drop a stone, and it falls to the floor, just as it always does. You wonder why. Is it because the stone is drawn to the Earth's heart, as the scholars say? Or is there another force at play, something simpler, something that doesn't require a round Earth spinning through the heavens? This question, this curiosity about why things fall, is as old as human thought. It's a question that has driven philosophers, scientists, and dreamers to seek answers, and it's at the heart of the Flat Earth movement's challenge to gravity. As we explore this paradox, we'll weave together science, history, and philosophy, not to argue for one truth over another, but to understand why the idea of defying gravity captivates us, and what it reveals about our quest to make sense of the cosmos. The gravity defiance paradox begins with a simple observation. Things fall downward. A leaf drifts from a tree, a ball rolls off a table, and a raindrop splashes on the ground. In mainstream science, this phenomenon is explained by gravity, a force exerted by the Earth's mass that pulls objects toward its center. Gravity is why we don't float away into space, why the oceans stay in their basins, and why the moon orbits the Earth. It's a universal force, described by Isaac Newton in the 17th century and refined by Albert Einstein in the 20th century, who envisioned gravity as the curvature of space-time caused by massive objects. For a spherical Earth, gravity makes perfect sense. The planet's mass creates a force that acts inward toward the core, ensuring that everything, People, buildings, oceans stays in place no matter where they are on the globe's surface. Flat Earth models, however, reject this concept of gravity, arguing that it's unnecessary or even fabricated to support the idea of a spherical planet. Instead, they propose alternative explanations for why things fall, often rooted in concepts like density, buoyancy, or upward acceleration. Let's explore these alternatives one by one, as if we're peeling back the layers of a cosmic mystery to understand their appeal and their limitations. One common flat Earth explanation is that objects fall because of density and buoyancy, not gravity. In this view, the Earth is a flat plane, and objects move downward because denser materials naturally sink through less dense mediums, like air. Imagine a rock in a pool of water. The rock sinks because it's denser than the water, while a cork floats because it's less dense. Flat Earth proponents extend this idea to the air around us, suggesting that objects like a pen or a stone fall because they're denser than the air, and there's no need for a mysterious force like gravity. This explanation feels intuitive because it aligns with everyday experiences. Things do seem to sort themselves by density in water or air, but it falls apart under scrutiny. Density and buoyancy alone can't explain why objects fall at a consistent rate, regardless of their density. A feather and a hammer, dropped in a vacuum where air resistance is absent, fall at the same speed, as demonstrated by astronaut David Scott on the Moon in 1971. This is because gravity, not density, governs their motion. Moreover, the density model struggles to account for why objects fall downward specifically, rather than in any other direction, or why the force of falling weakens with altitude, as measured on mountaintops or in airplanes. Another flat Earth proposal is even more audacious. The Earth itself is accelerating upward through space, creating the illusion of gravity. Picture yourself in a car that's speeding upward, pressing you against the seat. In this flat Earth model, the flat plane of the Earth is like the floor of that car, constantly accelerating at 9.8 meters per second squared, the same rate as Earth's gravitational acceleration. This upward motion, proponents argue, pushes objects toward the Earth's surface, mimicking the effect of gravity. The analogy is compelling because it feels plausible. If you're in an accelerating elevator, you feel pressed against the floor as if a force is pulling you down. But this idea unravels when we consider the broader implications. For the Earth to accelerate upward indefinitely, it would need an infinite source of energy, and it would eventually approach the speed of light, which Einstein's theory of relativity shows is impossible for objects with mass. Additionally, this model can't explain why gravity varies slightly across the Earth's surface, stronger at the poles, weaker at the equator, or why it weakens with altitude, as measured by precise instruments. The upward acceleration idea also struggles to account for the Coriolis effect, a phenomenon caused by the Earth's rotation that influences weather patterns and ocean currents, which a flat, accelerating plane wouldn't produce. To make this clearer, let's use an analogy. Imagine you're on a giant escalator, moving upward at a steady rate. You drop a ball, and it falls to the escalator's floor because the floor is rushing up to meet it. This is how the flat Earth acceleration model envisions the Earth's motion. Now, compare this to the scientific view, where the Earth is like a massive magnet, pulling objects toward its center with a force that depends on their mass and distance. The escalator analogy captures the flat Earth model simplicity, but it fails to explain the complexity of gravitational effects, like the way planets orbit the sun or the precise measurements of gravity's variations across the globe. The scientific model, while less intuitive, accounts for these phenomena with remarkable accuracy, from the tides to the trajectories of spacecraft. Historically, the concept of gravity was a turning point in affirming a spherical Earth. In the late 17th century, Isaac Newton formulated his law of universal gravitation, proposing that every object with mass attracts every other object, with a force proportional to their masses and inversely proportional to the square of the distance between them. Newton's theory explained why apples fall, why the moon orbits the Earth, and why the planets follow elliptical paths around the sun. It was a revolutionary idea, uniting terrestrial and celestial phenomena under a single force. Newton's work built on earlier observations, like those of Galileo, who studied falling objects and showed that they accelerate at a constant rate regardless of their mass, in the absence of air resistance. These discoveries solidified the spherical Earth model, as gravity's inward pull made sense for a globe, not a flat plane. By the 20th century, Einstein's general relativity refined gravity as a curvature of space-time, further confirming the spherical Earth within a dynamic universe. Flat Earth proponents, however, challenge this foundational concept, arguing that gravity is a construct of mainstream science designed to uphold the globe model. They point to the intuitive appeal of density or acceleration, claiming these explanations are simpler and more aligned with common sense. Some even cite anomalies, like objects appearing to fall at slightly different rates in certain conditions, as evidence against gravity. Science counters these claims with rigorous evidence. Gravitational variations are mapped with precision, as seen in NASA's GRACE mission, which measures Earth's gravity field. Experiments, like those using pendulums or gravimeters, confirm gravity's consistency with a spherical Earth. Yet, the gravity defiance paradox persists because it taps into a deeper human instinct, the desire to trust what feels immediate and observable over abstract theories. Let's deepen this with another analogy. Imagine you're a sailor on a calm sea, dropping a stone into the water. It sinks, and you assume it's because the water is pushing it down or because the stone is heavier than the sea. This is the flat Earth density model in action. Simple, visceral, rooted in what you see. Now, imagine a scientist aboard your ship, explaining that the stone falls because the Earth's mass creates an invisible force, pulling everything toward its center. The scientist's explanation requires you to imagine a spherical planet, a force you can't see, and a cosmos governed by mathematics. The sailor's view feels truer because it's tangible, but the scientist's view explains not just the stone, but the tides, the stars, and the orbits of distant worlds. The gravity defiance paradox is this clash of perspectives, a tension between the immediate and the universal. The gravity defiance paradox is more than a debate about why things fall. It's a profound challenge to the invisible forces that shape our reality. If gravity, as science describes it, isn't what we think, what other foundational truths might be misconceptions? This question strikes at the heart of how we understand the world, forcing us to confront the reliability of our senses, our science, and our beliefs. Gravity is one of those rare concepts that feels both deeply personal and cosmically vast. It's the force that keeps your feet on the ground, but it's also the force that binds galaxies together. To question it is to question the very fabric of existence. And that's what makes this paradox so unsettling, yet so compelling. Let's linger on this unease. Imagine waking up tomorrow to find that gravity, as you've known it, doesn't exist. Objects fall, but not because of a force pulling them toward a spherical Earth's core. Instead, the ground is rising to meet them, or they're sinking through air like stones in water. The world feels different, not just physically but philosophically. Without gravity, the Earth might not be a globe spinning through space, but a flat stage, a platform moving through an unknown cosmos. This reimagination is both liberating and disorienting. It frees you from the complexity of modern science, offering a simpler explanation for the world's mechanics. But it also unmoors you, challenging the evidence of countless experiments, observations, and technologies, GPS, satellites, lunar landings, that rely on gravity's existence. The gravity defiance paradox asks, how do we choose between a narrative that feels intuitive and one that's backed by rigorous proof? This tension highlights a broader theme, the clash between empirical evidence and alternative narratives. Gravity is one of science's most tested concepts, supported by centuries of data, from Newton's falling apple to the precise orbits of spacecraft. Yet, flat Earth theories reject it, prioritizing explanations that align with direct experience. This rejection isn't just about science, it's about trust. In an age of skepticism, where institutions, governments, scientists, media are often questioned, The idea of gravity as a lie resonates with those who feel the world's truths are being hidden. The gravity defiance paradox becomes a symbol of resistance, a way to reclaim agency by trusting one's own reasoning over expert pronouncements. But this resistance comes with a challenge. How do we validate truth when our instincts and evidence diverge? How do we navigate a world where the invisible forces we take for granted might be illusions? Philosophically, the paradox touches on epistemology, the study of knowledge and how we acquire it. Gravity is invisible, intangible, yet we accept it because its effects are measurable and predictable. Flat Earth alternatives, like density or acceleration, feel more tangible because they rely on visible phenomena, sinking, rising, moving. This contrast mirrors a classic philosophical debate. Do we know the world through our senses or through reason? The Greek philosopher Plato argued that sensory experience is deceptive, like shadows on a cave wall, and true knowledge comes from intellectual insight. The gravity defiance paradox echoes this, asking whether we trust the shadow of falling objects or the deeper insight of scientific models. It's a question that feels both ancient and urgent, especially in a world where competing narratives vie for our belief. The paradox also invites existential reflection. Gravity grounds us, literally and metaphorically. It's the force that keeps us tethered to the Earth, a reminder of our connection to the planet and the cosmos. To deny gravity is to rethink that connection, to imagine a world where we're not orbiting a star in a vast universe, but standing on a flat plane, perhaps at the center of creation. This vision is comforting, suggesting a cosmos designed with purpose, where humanity holds a special place. But it's also unsettling, because it requires dismissing the evidence that places us in a larger, more indifferent universe. What does it mean to be grounded in a world without gravity? What anchors us, not just physically, but emotionally and spiritually, when the forces we rely on are called into question? Let's pause here, as the video's soothing tone encourages reflection. Take a slow, deep breath and feel the surface beneath you, your bed, your chair, the floor. Notice the gentle pressure holding you in place, the quiet assurance of the Earth's pull. Now imagine that pull isn't gravity, but something else, an upward rush, a sinking through air, a cosmic dance. What does that shift feel like? Does it make the world seem simpler or more mysterious? As you listen, perhaps in the dim light of evening, let this question linger. What keeps you grounded, literally and metaphorically? This moment of stillness, this invitation to ponder, is part of the journey, a chance to let the gravity defiance paradox settle into your thoughts like a soft whisper in the night. The implications of this paradox extend beyond science and philosophy into the realm of human curiosity. It's a reminder that questioning the obvious, why things fall, why the world feels stable, can lead to profound insights, even if the answers challenge our assumptions. The flat Earth rejection of gravity, while scientifically untenable, reflects a deeper human impulse to seek explanations that resonate with our experience, to find meaning in the forces that shape our lives. It's a call to humility, to recognize that our understanding of the world is built on centuries of inquiry, and that even the most certain truths, like gravity, were once mysteries. As you drift towards sleep, let the gravity defiance paradox be a gentle nudge, a reminder to stay curious, to keep asking what holds the world together. As we rest in the quiet mystery of the forces holding us to the Earth, our minds filled with questions about gravity, density, and the nature of our reality, let's turn our gaze to another flat Earth claim. If the Earth is a flat plane, how do the sun and moon move above it? What secrets do their paths reveal about the cosmos? Let's explore a celestial puzzle that dances across the sky, inviting us deeper into the enigma of a flat Earth. Imagine waking at dawn, the first light of morning creeping through your window, painting the world in hues of gold and pink. You step outside, and there it is, the sun, rising in the east, a radiant orb climbing slowly into the sky. It arcs across the heavens, casting warmth and shadows, before sinking into the west, leaving a trail of twilight in its wake. This daily journey of the sun is one of the most familiar rhythms of life, a constant that has guided farmers, sailors, and poets for millennia. On a spherical Earth, this motion is elegantly simple. The planet rotates on its axis every 24 hours, turning us toward and away from the sun, creating the cycle of day and night. But what if the Earth isn't a globe? What if it's a flat plane, stretching out beneath a different kind of sky? How then does the sun move? How does a flat Earth explain this celestial dance that shapes our days? In flat Earth cosmology, the sun's journey is reimagined in a way that's both bizarre and mesmerizing. The sun is not a distant star, 93 million miles away, but a small local light source, circling above the flat Earth like a lantern on a track, illuminating specific regions as it moves. This idea of a local sun orbiting over a planar Earth challenges everything we've been taught about the cosmos, yet holds a strange allure, a poetic simplicity that feels almost mythical. It's as if the sun were a divine spotlight, designed to shine on us, to mark the hours of our lives with purpose. In this segment, we'll explore the sun's strange path, not to champion or dismiss the flat Earth view, but to unravel its fascination. We'll weave through the interplay of observation and imagination, science and storytelling, to understand why this vision of the sun captivates and what it reveals about our place beneath the heavens. So, take a slow breath, picture the sun's arc across today's sky, and let's embark on this peculiar journey, a mystery that glows with both wonder and paradox. Picture yourself as an ancient astronomer, standing on a windswept hill under a starlit night, your eyes tracing the sun's path from memory. You've watched it rise and set, day after day, and you've begun to wonder, what moves the sun? Is it a god in a chariot, as your people believe, or something else, a mechanism, a cycle, a light circling above the flat Earth, This question, this curiosity about the sun's motion, is as old as humanity itself. It's a question that has sparked myths, philosophies, and scientific revolutions, and it's at the heart of the flat Earth model's reimagination of the sun. As we delve into this mystery, we'll explore how the sun's strange path challenges our understanding of the cosmos, blending the intuitive with the improbable, and inviting us to question the scale, purpose, and design of the world we inhabit. In flat Earth cosmology, the sun is envisioned as a small, local light source, perhaps only a few miles across, suspended above the Earth's flat surface, moving in a circular or spiral path centered around the North Pole. Unlike the scientific model, where the sun is a massive star, 1.4 million kilometers in diameter, located 149.6 million kilometers, 93 million miles, from Earth, the flat Earth sun is intimate, almost tangible, a beacon that orbits the plane of the Earth to create day and night. In this model, the Earth is a flat disk, with the North Pole at its center and the continents radiating outward, encircled by an icy barrier often called the Ice Wall, Antarctica in scientific terms. The sun, along with the moon, is said to circle above this plane, moving closer to or farther from different regions, illuminating some areas while leaving others in darkness. This motion is what flat Earth proponents claim explains the cycle of day and night, the changing seasons, and the variations in sunlight across the globe. To understand this concept, let's paint a vivid picture. Imagine the Earth as a vast, circular stage, with the North Pole as its center, like the hub of a wheel. Above this stage, a few thousand feet or miles up, the sun is a spotlight, not unlike one you'd see in a theater, shining downward in a focused beam. As the sun moves in a circular path around the North Pole, its light sweeps across the stage, illuminating different regions at different times. When the sun is directly above your part of the stage, it's noon, and the light is bright and warm. As it moves away toward another region, your area falls into dusk and then night, while another part of the stage is bathed in daylight. The sun's path might tighten or widen, proponents argue, to explain the seasons, a tighter circle in summer, bringing it closer to the North Pole and creating longer days in the northern hemisphere, and a wider circle in winter, shifting light southward. This model contrasts sharply with the scientific explanation of the sun's motion. In the mainstream view, the Earth is a spherical planet, rotating on its axis once every 24 hours, which causes the sun to appear to rise in the east and set in the west. The Earth also orbits the sun once a year, tilted at an angle of 23.5 degrees, which creates the seasons as different parts of the planet receive varying amounts of sunlight. The sun itself is a star with a mass 333,000 times that of Earth, burning at millions of degrees and powering life through photosynthesis. Its apparent motion across the sky is an illusion of perspective, caused by the Earth's rotation, not by the sun physically moving above us. This scientific model explains a wide range of phenomena. The consistent size of the sun in the sky, due to its immense distance, the predictable timing of sunrise and sunset, the geometry of solar eclipses, and the existence of time zones, which align with the Earth's curvature. The flat Earth model, however, struggles to account for these observations. Let's explore why, using the spotlight analogy to guide us. If the sun were a local light source, moving above a flat plane, its size and brightness should change as it approaches or recedes from an observer. A spotlight appears larger and brighter when it's closer, smaller and dimmer when it's farther away. Yet, the sun remains the same apparent size throughout the day, from sunrise to sunset, because it's so far away, 93 million miles, that its distance from any point on Earth barely changes. Flat Earth proponents might argue that atmospheric effects or the dome's properties maintain the sun's apparent size, but this adds complexity to an already strained model. Similarly, the local sun model fails to explain solar eclipses, where the moon passes precisely between the Earth and sun, casting a shadow with geometric precision that matches a spherical Earth and distant sun. On a flat plane, the sun and moon's paths would need to align in ways that defy consistent observation. Time zones pose another challenge. On a spherical Earth, time zones arise because the planet's rotation exposes different regions to sunlight at different times, creating a 24-hour cycle across 360 degrees of longitude. In the flat Earth model, the sun's spotlight would need to illuminate specific regions while leaving others in darkness, but this doesn't align with the gradual progression of daylight across the globe. For example, when it's noon in New York, it's 5 p.m. in London and 2 a.m. in Tokyo, a pattern that fits a rotating globe but is harder to reconcile with a circling sun above a flat plane. The seasons, too, are problematic. The Earth's axial tilt explains why the northern and southern hemispheres experience opposite seasons, but a local sun's changing circles would struggle to produce the same consistent, mirrored patterns across a flat Earth. Historically, the sun's motion was a key factor in the shift from flat to spherical cosmologies. Ancient cultures, like the Babylonians and Egyptians, often envisioned a flat Earth with the sun moving above it, sometimes carried by gods or chariots. By the 6th century BCE, Greek philosophers like Pythagoras began proposing a spherical Earth, noting that the sun's path, the changing constellations, and the curved shadow during lunar eclipses suggested a globe. In the 3rd century BCE, Eratosthenes measured the Earth's circumference by comparing the sun's shadows in two cities, a calculation that assumed a spherical planet and a distant sun. By the 16th century, Copernicus's heliocentric model, which placed the sun at the center of the solar system, further solidified the spherical Earth, explaining the sun's apparent motion as a result of Earth's rotation and orbit. These discoveries, built on observation and mathematics, replaced flat cosmologies with a model that accounted for the sun's behavior with precision. Yet, the flat Earth vision of a local sun persists, fueled by its intuitive appeal. Proponents argue that the sun's path feels more like a nearby object circling above us than a distant star we're spinning toward and away from. They might point to the sun's apparent motion, its daily arc, as evidence of a simple, contained system, or claim that scientific models rely on unprovable assumptions about distance and scale. Science counters with overwhelming evidence. Telescopes reveal the sun's surface features, like sunspots, consistent with a massive star. Spacecraft, like NASA's Parker Solar Probe, have approached the sun, measuring its properties at distances that align with a 93 million-mile journey. The flat Earth model, while evocative, requires dismissing these observations or invoking additional mechanisms, like a dome or atmospheric effects, that lack empirical support. Let's deepen this with another analogy. Imagine you're in a vast, dark room, and a small lamp is moving in a circle above a flat table. As the lamp passes overhead, it lights your area brightly, then dims as it moves away, casting light elsewhere. This is the flat Earth sun, a local source illuminating a plane. Now, contrast this with the scientific view. You're on a rotating platform, spinning slowly under a distant, massive spotlight that never moves. The light seems to shift because you're turning, not because the spotlight is circling. The first scenario feels simpler, more immediate, but the second explains why the light's size and intensity remain constant, why its shadows align with a curved surface, and why its timing matches a global pattern. The sun's strange path, in flat Earth terms, is a story of simplicity, but it bends under the weight of the cosmos's complexity. The sun's strange path is more than a cosmological curiosity. It's a profound challenge to our understanding of scale, perspective, and purpose. If the sun were truly a local light source circling above a flat Earth, what would that mean for our place in the cosmos? This question strikes at the heart of how we see ourselves, not just as inhabitants of a planet, but as beings within a universe that might be designed indifferent or something else entirely. The flat Earth model, with its intimate sun, offers a vision of a cosmos that's centered on humanity, where the sun exists to illuminate us, to mark our days and seasons with deliberate care. It's a vision that feels deeply comforting, like a return to childhood stories where the world revolves around you. But it clashes with the vastness of scientific discovery, which places us on a small, spinning rock orbiting a star in a galaxy among billions. The tension between these perspectives, between a local sun and a distant star, invites us to explore the very nature of our existence. Let's linger on this idea of scale. In the flat Earth model, the sun is small, perhaps a few miles across, and close, maybe a few thousand miles above the Earth. This shrinks the cosmos to a human scale, making it feel knowable, contained, like a room with a glowing lamp. The scientific sun, by contrast, is colossal, with a diameter 109 times that of Earth, and so distant that its light takes 8 minutes to reach us. This scale is almost unimaginable, placing us in a universe where we're a tiny speck, our planet one of many orbiting one of countless stars. The local sun feels personal, purposeful, as if it were crafted for us. The distant sun feels humbling, reminding us of our smallness in an infinite expanse. Which vision resonates more? Does the sun's arc today feel like a nearby lantern, guiding your path, or a far-off giant, indifferent to your existence? This question touches on philosophy, particularly the debate over anthropocentrism, the idea that humans are the center of the universe. The flat Earth sun, circling above a flat plane, is anthropocentric to its core, suggesting a cosmos designed with us in mind. Ancient cosmologies, like those of the Greeks or Hebrews, often placed humanity at the universe's heart, with the sun and stars serving divine or practical purposes. The scientific revolution, beginning with Copernicus, challenged this, decentering Earth and humanity in favor of a heliocentric, then galactic, then universal model. The flat Earth sun is a rebellion against that shift, a return to a human-centered cosmos. But this return raises a challenge. If the sun is local, why does it behave with the precision of a distant star? Why do its eclipses, shadows, and seasons align with a spherical Earth in a vast universe? The sun's strange path also raises existential questions about purpose. In the flat Earth model, the sun's motion feels intentional, like a clock set to govern our lives. It rises and sets for us, creating a rhythm that feels personal, meaningful. In the scientific model, the sun's motion is an illusion of Earth's rotation, a byproduct of physical laws that operate without regard for human needs. This contrast mirrors a deeper question. Is the universe purposeful, or is meaning something we impose on it? The local sun offers a comforting narrative, a world where we're not just cosmic accidents, but central actors in a design system. But that comfort comes at a cost, requiring us to dismiss the evidence, space probes, telescopes, mathematical models, that reveals a grander, more impersonal cosmos. What does it mean to seek purpose in a universe that might not be built for us? What does it mean to find meaning in the sun's arc, whether it's a lantern or a star? Let's explore this through a historical lens. In the 2nd century CE, Ptolemy's geocentric model placed Earth at the universe's center, with the sun and planets orbiting in complex paths. This model dominated for over a millennium, aligning with both observation and theology. Copernicus's heliocentric model, published in 1543, upended this, placing the sun at the center and Earth in motion. The shift was not just scientific, but philosophical, challenging humanity's sense of centrality. The flat Earth-sun, with its local orbit, echoes Ptolemy's vision, reviving a cosmos where we're the focal point. But it struggles against the weight of evidence, from Eratosthenes' shadow measurements to modern satellite imagery, that supports a spherical, rotating Earth. The sun's strange path is a reminder that scientific progress often requires us to let go of comforting narratives, even as we yearn for them. Psychologically, the local sun taps into our need for connection. The sun is more than a star. It's a symbol of life, warmth, and continuity. To imagine it as a nearby light, circling just for us, is to feel seen, cared for, part of a purposeful design. The scientific sun, distant and massive, can evoke awe but also isolation, a sense of being adrift in a vast, uncaring universe. The flat Earth model counters this with a sense of intimacy, but it raises a question. Are we drawn to the local sun because it's true, or because it soothes our existential fears? Are we seeing the sun as it is, or as we wish it to be? Let's pause here, as the video's meditative tone invites reflection. Close your eyes, if you like, and picture the sun's arc today. Maybe you saw it rise over a horizon of trees, or set behind a city skyline. Its light soft and fleeting. Does it feel close, like a lantern hung, just for you, or vast, a star too grand to fathom? What does its journey mean to you? Not just as a celestial body, but as a presence in your life. As you listen, perhaps in the quiet of evening, let this question settle into your thoughts, a gentle glow in the darkness. The sun's strange path is not just a puzzle. It's a mirror, reflecting our longing for meaning, our curiosity about the cosmos, and our place beneath its light. The implications of this paradox extend beyond astronomy into the realm of human experience. The sun's path, whether local or distant, shapes how we see ourselves, central or peripheral, purposeful or incidental. It's a call to wonder, to question the stories we tell about the world, and to balance intuition with evidence. As you drift towards sleep, let the sun's strange path be a quiet invitation, a chance to ponder the mysteries that light our days. As we rest in the glow of the sun's curious journey, our minds filled with questions about its path and our place beneath it, let's turn our gaze to another celestial companion. The moon, with its soft, silvery light, holds its own secrets in flat Earth cosmology. How does it move? And what does its glow reveal about the world? Let's explore a lunar mystery that shimmers in the night, drawing us deeper into the enigma of a flat Earth. Picture yourself on a quiet night, stepping outside into the cool embrace of darkness. The world is hushed, save for the soft rustle of leaves or the distant call of a night creature. You tilt your head back, and there it is, the moon, hanging in the sky like a silver coin, its soft, silvery light casting a gentle glow over the landscape. Its surface is etched with shadows, craters, and seas that seem to whisper stories of ancient times. For millennia, the moon has captivated humanity, inspiring myths, poetry, and dreams. It's been a goddess, a guide, a symbol of mystery and wonder. Its light feels different from the sun's, cooler, quieter, almost otherworldly, as if it carries secrets from a realm beyond our own. But what is the source of this glow? In the scientific story, the moon is a rocky satellite, orbiting Earth at a distance of 384,000 kilometers, reflecting sunlight to create its phases. Yet, in flat Earth cosmology, the moon is reimagined as something far stranger, a self-luminous object, perhaps emitting its own light, or even a holographic projection on a celestial dome. Why does the moon's glow feel so mystical, so unlike anything else in the sky? Why do flat Earth theories reject the idea of reflected sunlight, proposing instead a moon that shines with its own radiance or exists as a cosmic illusion? This concept, the moon's mysterious glow, is not just a challenge to astronomy. It's a doorway into the human psyche, a reflection of our fascination with the unknown and our desire to find meaning in the heavens. In this segment, we'll explore the moon's enigmatic light, not to argue for one truth over another, but to unravel its allure. We'll journey through the interplay of science and myth, observation and imagination, to understand why the moon's glow captivates us and what it reveals about our longing for a cosmos that feels both magical and intimate. So, take a slow, deep breath, let the image of the moon fill your mind, and let's drift into this mystery, a silvery enigma that shimmers in the night. Imagine yourself as a storyteller in an ancient village, gathered around a fire under a full moon's glow. Your listeners, young and old, lean in as you describe the moon, not as a distant rock, but as a divine lantern hung by the gods to light the night. Its glow, you say, is its own, a gift to guide travelers and dreamers. The story feels true because the moon's light seems so unique, so unlike the harsh brilliance of the sun. This vision, this belief in a self-luminous moon, echoes through flat Earth theories today, tapping into the same sense of wonder that has always surrounded our closest celestial companion. As we delve into this paradox, we'll ask, what makes the moon's glow so compelling? How does flat Earth cosmology reimagine it? And what does this reimagination reveal about our relationship with the night sky? In flat Earth cosmology, the moon is not a natural satellite orbiting a spherical Earth, but a mysterious object with its own unique properties, often described as self-luminous or even a projection on a celestial dome. Unlike the scientific model, which sees the moon as a rocky body, roughly 3,474 kilometers in diameter, orbiting Earth at an average distance of 384,000 kilometers and reflecting sunlight to create its phases, flat Earth theories propose a radically different vision. The moon, they argue, emits its own light, independent of the sun, or exists as a holographic or ethereal image, perhaps projected onto a firmament, a dome-like structure encasing the flat Earth. This idea draws from ancient cosmologies and modern skepticism, fueled by the moon's ethereal glow and its seemingly unique place in the sky. Proponents often cite the moon's cold light, which feels less intense than sunlight, or alleged inconsistencies in shadow patterns during eclipses, as evidence that the moon's light is not reflected but self-generated. To understand this concept, let's begin with the flat Earth perspective. In their model, the Earth is a flat plane, with the North Pole at its center and the continents radiating outward, encircled by an icy barrier. Above this plane, the sun and moon are small, local objects, perhaps a few miles across, circling in paths around the North Pole, suspended a few thousand miles above the surface. The moon, in this view, does not reflect sunlight but shines with its own radiance, like a cosmic lamp. Some flat Earth enthusiasts go further, suggesting the moon is a projection, a kind of hologram displayed on the dome, controlled by unknown forces or entities. They point to the moon's phases, its waxing and waning, as evidence of a programmed cycle, not a result of sunlight illuminating a spherical body. Others claim the moon's light has unique properties, like a cooling effect, contrasting with the sun's warming rays, and cite anecdotal observations, such as the clarity of shadows cast by moonlight, as proof of its distinct nature. Let's explore this with an analogy. Imagine you're in a darkened room, holding a flashlight. You shine it on a mirror, and the light bounces back, illuminating a spot on the wall. This is the scientific moon, a mirror reflecting the sun's light. Its glow, a redirected beam from a distant star. Now, imagine instead a glowing orb in the room, emitting its own soft light, like a paper lantern. This is the flat Earth moon, a self-luminous source, independent and mysterious, casting its glow without needing another light to shine. The mirror analogy aligns with science, but the lantern captures the flat Earth's poetic vision, a moon that feels alive, purposeful, a beacon in the night. This vision taps into the moon's mystique, its ability to evoke wonder and otherworldliness, making the idea of a self-luminous moon feel intuitive, even if it defies evidence. In scientific terms, the moon's glow is well understood. The moon is a natural satellite, its surface covered in dust and rock that reflects sunlight with an albedo, reflectivity, of about 12%. Its phases, new, crescent, quarter, gibbous, full, are caused by the changing angles between the Earth, Moon, and Sun as the Moon orbits every 27.3 days. When a moon is between the Earth and Sun, we see the dark new moon. When it's opposite the Sun, we see the fully illuminated full moon. This model explains the moon's predictable cycle, its role in eclipses, and its gravitational influence on tides. Spectroscopy, a technique that analyzes light's wavelengths, confirms that moonlight is reflected sunlight with the same spectral signature as the sun's rays, adjusted for the moon's surface composition. Lunar missions, like NASA's Apollo program, 1969 to 1972, returned 382 kilograms of moon rocks, proving the moon is a physical body, not a projection. Spacecraft, like the Lunar Reconnaissance Orbiter, have mapped its surface in detail, revealing craters, mountains, and plains consistent with a rocky satellite. Flat Earth claims, however, challenge this narrative. Proponents argue that moonlight feels cold compared to sunlight, citing anecdotal experiences of cooler temperatures under moonlight. They may point to the umbral shadow during lunar eclipses, claiming inconsistencies in how Earth's shadow falls on the moon, or suggest that moonlight's clarity, its ability to cast sharp shadows, indicates a different kind of light. Some even reference ancient texts, like the Bible's description of the moon as a lesser light, Genesis 1 verse 16, as evidence of its independent glow. These arguments are debunked by science. Moonlight feels cooler because it's far less intense than sunlight, delivering only about 0.0001% of the sun's energy. Eclipse shadows follow precise geometry, predictable by orbital mechanics. The moon's sharp shadows result from its lack of an atmosphere, which scatters light on Earth, softening shadows. Yet, the flat Earth moon persists because its glow feels so distinct, so magical, that it invites alternative explanations. Historically, the moon's role in cosmology has evolved dramatically. Ancient cultures, like the Sumerians and Greeks, often saw the moon as a deity or divine light, governing night and influencing human affairs. In Mesopotamian mythology, the moon god Sin was a source of wisdom, his light a gift to humanity. The Greeks, by the 4th century BCE, began to view the moon as a physical body, with Aristotle suggesting it reflected sunlight. By the 17th century, Galileo's telescope revealed the moon's craters and mountains, cementing its status as a rocky world. The Apollo missions, which landed humans on the moon, marked a scientific triumph, proving its physical reality. Yet, the moon's mystique endures, fueling flat Earth theories that revive ancient visions of a self-luminous or ethereal moon, blending spirituality with skepticism of modern science. Let's deepen this with another analogy. Imagine the moon as a silver mirror in a grand hall, reflecting the light of a distant chandelier, the sun. Its glow is borrowed. Its phases a dance of angles and shadows. Now, picture it as a glowing crystal, suspended in the air, radiating its own light, independent and alive. The flat Earth moon is this crystal, a source of wonder that feels closer, more personal than a distant rock. The scientific moon, while grounded in evidence, lacks this poetic immediacy, making the flat Earth vision appealing to those who see the moon as more than matter. This contrast between mirror and crystal captures the heart of the moon's mysterious glow, a paradox that blends observation with imagination. The idea of a self-luminous or projected moon is more than a cosmological oddity. It's a profound challenge to our trust in the tools and methods we use to understand the universe. If the moon isn't a rocky satellite reflecting sunlight, as science claims, what else might be an illusion? This question shakes the foundations of our knowledge, inviting us to question the reliability of telescopes, spacecraft, and the scientists who wield them. The flat Earth moon, with its ethereal glow, suggests a cosmos where appearances might deceive, where the heavens could be a stage, a projection, or a divine creation rather than a measurable reality. This possibility is both unsettling and exhilarating, a call to explore the boundaries between science and spirituality, evidence and intuition. Let's linger on this challenge to trust. The scientific moon is built on centuries of observation and exploration. Telescopes reveal its surface in stunning detail, from the Sea of Tranquility to the Tycho crater. Spectroscopy confirms its light is reflected sunlight, with no unique emissions. The Apollo missions brought back physical proof, moon rocks analyzed in labs worldwide. Yet, the flat Earth moon dismisses this, proposing a light or projection that defies these tools. This rejection isn't just about the moon, it's about the scientific enterprise itself. If we can't trust the evidence of lunar landings, what can we trust? If the moon's glow is a hologram, what else in our reality might be staged? This idea taps into a broader skepticism, a distrust of institutions, NASA, governments, academia, that resonates in an age of information overload and competing narratives. Philosophically, the moon's mysterious glow touches on the nature of reality and perception. The 17th century philosopher René Descartes famously questioned whether we could trust our senses, wondering if an evil demon might deceive us about the world. The flat Earth moon echoes this, suggesting the heavens might be a deception, a cosmic trick. This aligns with modern philosophical debates, like the simulation hypothesis, which posits that reality could be a computer-generated illusion. The self-luminous moon feels like a step toward this, a vision of a controlled, artificial cosmos. But it also clashes with empiricism, the belief that knowledge comes from observation and evidence. The scientific moon, with its rocks and orbits, is empirical. The flat Earth moon is intuitive, rooted in the glow's mystique. Which do we trust, the tools that measure or the feelings that inspire? The moon's glow also reflects humanity's fascination with the unknown, a blend of science and spirituality that has defined our relationship with the night sky. Across cultures, the moon has been a symbol of mystery, intuition, and the divine. In Hinduism, the moon god Chandra embodies calm and creativity. In Native American traditions, the moon guides cycles of nature. The flat Earth moon revives this spiritual dimension, imagining a light that's more than physics, a beacon, a presence. This vision is soothing, suggesting a cosmos that cares, where the moon's glow is a gift rather than a reflection. But it's also unsettling, because it requires us to question the tangible evidence of our explorations, from moon rocks to satellite imagery. What does it mean to embrace a moon that's a lantern rather than a rock? What does it mean to prioritize wonder over proof? Let's explore this through a historical lens. In the Middle Ages, the moon was often seen as a celestial sphere, reflecting divine light or influencing earthly events through astrology. The scientific revolution, with Galileo's telescope and Newton's laws, transformed it into a physical body, subject to the same forces as Earth. The Apollo landings were a pinnacle of this shift, turning myth into matter. The flat Earth moon resists this, reviving pre-scientific visions where the moon is a light, a symbol, a mystery. This resistance mirrors a broader tension, the pull between modernity's rationalism and humanity's longing for enchantment. The moon's glow, in flat Earth terms, is a call to reclaim that enchantment, even if it means setting aside the evidence of our own journeys. Psychologically, the self-luminous moon taps into our need for connection and meaning. The moon is more than a celestial body. It's a companion, a constant in our nights. To imagine it as a glowing lantern, independent and alive, is to feel seen, accompanied in the darkness. The scientific moon, distant and rocky, evokes all but also isolation, a reminder of our smallness in a vast universe. The flat Earth moon counters this with intimacy, but it raises a question: are we drawn to this vision because it's true, or because it comforts us? Are we seeing the moon as it is, or as we wish it to be? Let's pause here, as the video's meditative tone invites reflection. If you're listening in a quiet space, perhaps with the moonlight filtering through a window, picture the moon above you. Its glow is soft, silvery, a quiet presence. Does it feel like a companion, a friend who's always there, or a mystery, a puzzle you can't quite solve? What does its light mean to you? Not just as a celestial object, but as a presence in your nights. As you drift towards sleep, let this question linger, a gentle shimmer in your thoughts. The moon's mysterious glow is not just a paradox. It's a mirror, reflecting our curiosity, our dreams, and our longing for a cosmos that feels like home. The implications of this paradox extend beyond astronomy into the realm of human experience. The moon's glow, whether reflected or self-luminous, shapes how we see ourselves, connected or alone, grounded in evidence or lifted by wonder. It's a call to balance the tangible and the mystical, to honor both the rocks we've touched and the stories we tell. As you rest in this moment, let the moon's mysterious glow be a quiet invitation, a chance to ponder the mysteries that light our nights. As we linger in the soft radiance of the moon's glow, our minds filled with questions about its light and our place beneath it, let's shift our focus to the edges of the flat Earth. If the moon is a lantern or a projection, what lies beyond the known world? How do flat Earth theories imagine the boundaries of the plane we call home? Let's explore an enigma that stretches to the horizon, drawing us deeper into the mysteries of a flat Earth. Close your eyes and imagine standing at the edge of the world. The air is biting, sharp with the scent of frost, and before you looms a towering barrier of ice, its jagged peaks glistening under a pale, unending sky. This frozen wall stretches as far as you can see, an impenetrable fortress encircling the Earth, holding the oceans in place and guarding secrets beyond human reach. In flat Earth cosmology, this is the Ice Wall, a fantastical concept that reimagines Antarctica not as a continent, but as a massive, circular barrier at the edge of a flat, disc-like Earth. It's a vision both chilling and captivating, evoking ancient myths of forbidden lands and uncharted territories, where the known world ends and the unknown begins. Why does the idea of an ice wall grip the imagination? Why does it feel like more than a geographical claim, resonating as a symbol of mystery, protection, and hidden truths? In the scientific narrative, Antarctica is a continent, a frozen landmass roughly 14 million square kilometers in size, surrounded by the Southern Ocean and explored by scientists, adventurers, and even tourists. But in flat Earth theories, the ice wall is something else entirely, a boundary that defines the limits of our world, a wall that keeps the sea from spilling into the void and perhaps conceals what lies beyond. In this segment, we'll explore the Ice Wall Enigma, not to affirm or refute its existence, but to unravel its allure. We'll weave through the threads of myth, science, and human curiosity, asking what this frozen barrier represents and why it captivates those who dream of a flat Earth. So, take a slow, deep breath. Let the image of a towering ice wall fill your mind, and let's step into this mystery, a chilling enigma that marks the edge of the known. Picture yourself as an explorer in a bygone era, bundled in furs, sailing toward the southern reaches of the world. The sea grows rough, the air colder, and whispers among your crew speak of a great wall of ice, a barrier no ship can pass. Some say it's the end of the earth itself, others that it hides lands or truths forbidden to mortals. This story, this vision of an impassable southern boundary, is not new. It echoes through ancient maps, maritime legends, and modern flat Earth narratives. The ice wall is more than a physical claim. It's a symbol of the human desire to define the world's limits, to draw a line between the familiar and the unknown. As we delve into this paradox, we'll ask, what is the ice wall, and why does it hold such power over our imaginations? What does it reveal about our need for boundaries, both physical and metaphysical? In flat Earth cosmology, the ice wall is a central feature, a massive, circular barrier of ice that surrounds the flat Earth, encircling its continents and oceans like a colossal rampart. Unlike the scientific understanding of Antarctica as a continent at the southern pole of a spherical Earth, flat Earth models reimagine Antarctica as this ice wall, stretching endlessly around the perimeter of a disk-like plane. The Earth, in this view, is a flat surface with the North Pole at its center, the continents radiating outward, and the ice wall, sometimes called the Antarctic Rim, forming its outer boundary. This wall is said to rise hundreds or thousands of feet, holding the world's oceans in place and preventing them from spilling off the edge into whatever lies beyond, be it a void, an abyss, or an unknown realm. The ice wall is not just a geographical feature. It's a functional necessity, a structure that maintains the integrity of the flat Earth and, in some narratives, guards secrets kept from humanity. To visualize this, imagine the Earth as a vast, circular garden, its center marked by the North Pole, its fields and rivers, the continents and oceans spreading outward. At the garden's edge stands a towering wall of ice, like a frozen moat, encircling everything and keeping the waters contained. The sun and moon, in this model, circle above the plain, illuminating different regions, while the ice wall stands as a silent sentinel, defining the world's limits. Flat Earth proponents argue that this wall explains why no one can fall off the Earth and why exploration of Antarctica is restricted, often citing international treaties like the Antarctic Treaty of 1959 as evidence of a conspiracy to hide the wall's true nature. They may point to historical accounts of impenetrable ice barriers or claim that satellite images of Antarctica are fabricated, showing a continent when the reality is a continuous wall. In scientific terms, Antarctica is a well-documented continent, roughly twice the size of Australia, covered in ice sheets up to 4 kilometers thick. It's surrounded by the Southern Ocean, not a wall, and its coastline has been mapped by ships, planes, and satellites. Explorers like Roald Amundsen, who reached the South Pole in 1911, and modern scientists studying its ice cores and ecosystems have confirmed its status as a landmass, not a barrier. Satellite imagery, such as from NASA's MODIS or ESA's Sentinel missions, shows Antarctica's cohesive shape, with research stations like McMurdo and Amundsen Scott operating year-round. Ships and planes routinely cross its waters and airspace, and tourists visit its edges, experiencing a frozen continent, not an endless wall. The scientific model explains Antarctica's role in global climate, its influence on ocean currents, and its geological history, all consistent with a spherical Earth. The flat Earth ice wall, however, struggles to account for these observations. If Antarctica were a continuous wall encircling a flat Earth, why can ships sail around it, completing circumnavigations, as documented by explorers like James Cook in the 18th century? Why do flights, such as those from Chile to Australia, cross Antarctic airspace without encountering a barrier? Why do satellite images show a landmass with distinct features, mountains, glaciers, ice shelves, rather than a uniform wall? Flat Earth proponents might argue that these are illusions, part of a global cover-up, or that the wall lies beyond the explored regions of Antarctica, inaccessible due to military restrictions. The Antarctic Treaty, which bans military activity and promotes scientific cooperation, is often cited as evidence of secrecy, though it's publicly accessible and signed by 54 nations. Let's explore this with an analogy. Imagine your world is a walled garden, its boundaries marked by a high, icy fence that keeps the flowers and streams within. You can walk the garden's paths, but the fence is always there, defining the edge, protecting the known from the unknown. This is the flat Earth ice wall, a boundary that contains a limit that reassures. Now, contrast this with the scientific view. Your world is a globe, and Antarctica is a snowy island at its southern tip, surrounded by a vast ocean. You can sail around it, fly over it, study its rocks and ice, and see it from space. The garden analogy captures the ice wall's appeal, a finite, protected world, but it falters against the evidence of exploration, from Amundsen's trek to modern GPS mapping, which reveals a continent, not a wall. Historically, the ice wall draws from myths and maps that depicted the southern world as mysterious and forbidden. Ancient Greek philosophers like Ptolemy imagined a terra australis, a vast southern land to balance the northern continents, though they never saw it. Medieval maps, like the Mappa Mundi, placed Jerusalem at the world's center with unknown lands at the edges, sometimes guarded by ice or monsters. Early explorers, like Ferdinand Magellan, sailed southern waters, finding no wall but confirming the Earth's roundness. By the 19th century, Antarctic exploration revealed a frozen continent, not a barrier. Yet myths of an impassable edge persisted, fueled by tales of treacherous ice and restricted access. Flat Earth theories revive these myths, blending them with modern conspiracy narratives to create the ice wall, a symbol of a hidden truth at the world's end. The ice wall's appeal lies in its simplicity and symbolism. It offers a clear, tangible boundary, a way to make sense of flat Earth without needing complex forces like gravity to hold the oceans in place. It also taps into a sense of secrecy, suggesting that the wall hides something, perhaps new lands, cosmic truths, or evidence of a created world. Science counters with overwhelming evidence. Antarctica's geology, studied through ice cores dating back 800,000 years, shows a dynamic continent, not a static wall. Seismic data map its bedrock, and radar reveals subglacial lakes, inconsistent with a uniform barrier. Yet, the ice wall endures in flat Earth lore because it feels protective, mysterious, a line between the known and the unthinkable. Let's deepen this with another analogy. Imagine the Earth as a giant, circular table, its surface holding continents and seas. Around its edge runs a rim of ice, like the lip of a bowl, keeping everything contained. This is the flat Earth ice wall, a functional and symbolic edge. Now, picture the scientific Earth, a spinning ball, its southern pole a frozen land surrounded by water, open to exploration. The table analogy evokes the ice wall's contained world, but it can't explain why explorers cross Antarctica, why satellites see a continent, or why its ice flows in patterns consistent with the globe. The ice wall is a story of limits, but science tells a story of openness, a world without edges. The Ice Wall Enigma is more than a geographical claim. It's a profound exploration of human curiosity, fear, and the desire for a knowable world. If such a barrier exists, what might it hide? This question taps into our deepest instincts, evoking both wonder and unease. The ice wall suggests a finite Earth, a plane with clear boundaries, a cosmos that's contained and purposeful. It's a vision that feels comforting, like a walled garden shielding us from the chaos of the unknown. But it also challenges the spirit of discovery, the drive that sent explorers like Amundsen to the South Pole and scientists to map the stars. The ice wall is a paradox, a symbol of protection that invites speculation about what lies beyond, a boundary that both reassures and unsettles. Let's linger on the idea of secrecy. The ice wall, in flat Earth narratives, is often tied to conspiracy theories, with Antarctica portrayed as a restricted zone guarded by governments or shadowy forces. The Antarctic Treaty, which preserves the continent for peaceful research, is reframed as a cover-up, hiding the wall's true nature. This resonates in an age of distrust, where institutions are questioned and hidden truths are sought. If the ice wall exists, what might it conceal? New lands, as ancient maps imagined? A cosmic edge, where the flat Earth meets the dome or void? Or something more profound, like evidence of a designed world? This speculation fuels the ice wall's allure, turning it into a symbol of the unknown, a blank canvas for our fears and fantasies. Philosophically, the ice wall touches on the nature of boundaries and exploration. Humans have always sought to define the world's limits, from the here-be dragons of medieval maps to the modern mapping of the cosmos. The ice wall represents a hard limit, a point where exploration stops and the unknown begins. This concept resonates with the human impulse to impose order on chaos, to draw a line where the familiar ends and the mysterious starts. The ice wall, in its stark simplicity, offers a kind of existential clarity. The world is finite, contained, and knowable, with a clear edge marked by ice. But this clarity comes at a cost. It challenges the spirit of exploration that has driven humanity to cross oceans, climb mountains, and venture into space. If the ice wall exists, it suggests a world where some boundaries are absolute, where certain truths are forever out of reach. This tension between the comfort of limits and the yearning to transcend them is what makes the ice wall so compelling. It's a paradox that asks us to weigh the safety of a contained cosmos against the thrill of an open, infinite one. Consider the psychological allure of this boundary. The ice wall feels like a protective shield, a barrier that keeps the world intact, holding the oceans and continents in a secure embrace. There's something deeply soothing about imagining a finite Earth, where the edges are defined and the chaos of the unknown is kept at bay. It's like living in a walled city, safe from the wilderness beyond. Yet that same wall sparks curiosity, even fear. What lies on the other side? Is it a void, as some flat Earth models suggest, or a hidden realm guarded by forces we can't comprehend? The ice wall becomes a canvas for our imaginations, a place where we project our hopes for undiscovered lands, our fears of cosmic secrets, or our suspicions of a world manipulated by unseen powers. This duality, comfort and unease, mirrors the human condition, our simultaneous need for security and our drive to explore the unknown. The ice wall also raises profound questions about secrecy and access. In flat Earth narratives, the wall is often framed as a forbidden zone, a place where exploration is curtailed by international agreements or military presence. The Antarctic Treaty, signed in 1959 by 12 nations and now joined by 54, designates Antarctica as a continent for peaceful scientific research, banning military activity and mining. Flat Earth proponents, however, interpret this as evidence of a cover-up, arguing that the treaty hides the ice wall's true nature or restricts access to what lies beyond. This narrative taps into a broader cultural skepticism, a distrust of institutions that resonates in an era of misinformation and competing truths. If the ice wall is real, what might it conceal? Could it be a physical edge, a cosmic boundary, or even evidence of a created world, as some flat Earth advocates claim? The idea that something so monumental could be hidden in plain sight is both thrilling and unsettling, a reminder of how little we may truly know about the world. Let's explore this through a philosophical lens. The ice wall touches on the concept of epistemic boundaries, the limits of what we can know. The 18th century philosopher Immanuel Kant argued that human knowledge is constrained by the structures of our mind, that we can never know reality as it is, but only as we perceive it. The ice wall, in a sense, is a physical manifestation of this idea, a barrier beyond which knowledge stops, where the world becomes unknowable. In flat Earth cosmology, the wall marks the edge of human experience, a line we cannot cross. Science, however, rejects such limits, asserting that Antarctica is accessible, measurable, and part of a spherical Earth. The ice wall challenges us to consider where we draw the line between the knowable and the unknown between the evidence we trust and the mysteries we imagine. Do we accept the satellite images and explorer accounts, or do we entertain the possibility of a hidden boundary, a wall that guards truths we've yet to uncover? The ice wall also evokes a sense of nostalgia for a pre-modern worldview. Before the age of global exploration, the edges of the world were shrouded in myth. Maps from the Middle Ages, like the Tidal maps, depicted a flat Earth with Jerusalem at the center, surrounded by oceans and unknown lands. The southern reaches were often marked as terra ignota, unknown land, or guarded by fantastical barriers. The ice wall revives this vision, offering a return to a time when the world felt smaller, more contained, and more magical. But this nostalgia clashes with the reality of modern discovery. Antarctica has been studied for over a century, its ice cores revealing climate data stretching back 800,000 years, its wildlife, from penguins to seals, documented in detail. The ice wall, as a concept, asks us to choose between the enchantment of myth and the rigor of evidence, between a world with edges and one without. This choice carries existential weight. The ice wall suggests a cosmos that's finite, purposeful, and centered on humanity. It's a comforting thought, especially in moments of cosmic doubt, when the vastness of the scientific universe, 13.8 billion years old, 93 billion light-years wide, feels overwhelming. A flat Earth with an ice wall is a stage, a contained space where we're the central actors, not specks in an indifferent void. But this comfort requires dismissing the spirit of exploration that defines us. Humans have always pushed beyond boundaries, from Magellan's circumnavigation to the Apollo missions. The ice wall, by imposing an absolute limit, challenges that legacy, asking whether some frontiers are meant to remain unbreached. It's a question that resonates beyond geography, touching on our personal boundaries, where we draw the line between safety and adventure, certainty and curiosity. Let's deepen this with a cultural perspective. The ice wall draws on archetypes of forbidden boundaries found in literature and mythology. In Greek mythology, the Garden of the Hesperides was guarded by a dragon, its golden apples beyond mortal reach. In modern stories, like George R.R. Martin's Game of Thrones, the wall in the north is a frozen barrier separating civilization from the unknown. The flat Earth ice wall fits this archetype, a frozen frontier that both protects and provokes. It's a narrative device as much as a cosmological claim, inviting us to imagine what lies beyond, a new world, a cosmic truth, or simply nothing. This storytelling quality is what makes the ice wall so enduring, a symbol that transcends its physicality to speak to our deepest instincts. The ice wall also raises questions about power and control. If the wall exists and is hidden, who controls access? Flat Earth theories often point to governments, corporations, or shadowy elites, suggesting a global conspiracy to obscure the Earth's true shape. This narrative reflects a broader anxiety about transparency and autonomy in a modern world. The idea that Antarctica is a restricted zone, guarded to protect the ice wall's secret, empowers believers by positioning them as seekers of forbidden knowledge. But it also isolates them, pitting personal intuition against collective evidence. Science, with its open data, Antarctic research papers, satellite feeds, expedition logs, offers a counterpoint, inviting scrutiny rather than secrecy. The ice wall, then, becomes a battleground for trust. Do we believe the explorers who've crossed Antarctica or the storytellers who envision a wall? Let's pause here, as the video's meditative tone invites reflection. Picture yourself standing before a towering wall of ice, its surface glinting in the dim light of a polar sun. The air is cold, the silence profound. What do you feel as you gaze at this barrier? Is it a shield, keeping you safe, or a challenge, daring you to wonder what's beyond? Does it feel like the end of the world, or the beginning of a mystery? As you listen, perhaps in the quiet of your room, let this image linger in your thoughts, a frozen enigma that whispers of limits and possibilities. The ice wall is not just a concept. It's a mirror reflecting our need for boundaries, our fear of the unknown, and our endless curiosity about what lies just out of reach. The implications of the ice wall extend beyond cosmology into the realm of human experience. It's a reminder that boundaries, whether physical or intellectual, shape how we see the world. The ice wall offers a contained, knowable Earth, but it challenges the legacy of exploration that has defined humanity's progress. It's a call to balance the comfort of limits with the courage to push beyond them, to honor both the walls we build and the horizons we seek. As you drift towards sleep, let the Ice Wall Enigma be a gentle nudge, a chance to ponder the edges of your own world, where they lie, and whether you dare to cross them. As we stand before the imagined ice wall, our minds swirling with questions about boundaries, secrets, and the edges of the known, let's turn to another flat Earth mystery. If the Earth is a flat plane, how does it sustain the rhythm of day and night? What mechanism drives the sun and moon across the sky, creating the cycle that shapes our lives? Let's unravel a cosmic dance that defies conventional astronomy, drawing us deeper into the enigma of a flat Earth. As the sun dips below the horizon, painting the sky in hues of orange and purple, the world settles into the quiet embrace of night. Stars emerge, one by one, and the air grows cooler, wrapping you in a sense of calm. Hours later, dawn breaks, and the sun rises again, bathing the earth in golden light. This rhythm of day and night, this endless cycle of light and darkness, is one of the most fundamental patterns of existence. It shapes our lives, guides our routines, and whispers of a cosmos in motion. On a spherical Earth, this cycle is elegantly explained. The planet rotates on its axis every 24 hours, turning different regions toward and away from the sun, creating the dance of day and night. But what if the Earth isn't a globe? What if it's a flat plane, stretching out beneath a sky unlike the one we've been taught? How, then, do light and darkness alternate? How does a flat Earth sustain this ancient rhythm? In flat Earth cosmology, the day-night cycle is reimagined as a riddle, a puzzle that challenges our understanding of the heavens. Rather than a rotating globe, flat Earth models propose that the sun and moon move in circular paths above a flat plane, their light confined to specific areas, creating patches of day and night. The sun, in this view, is not a distant star illuminating half a globe, but a local light source, like a spotlight sweeping across a stage. This idea is both mind-bending and strangely poetic, evoking a cosmos that feels intimate, contained, and purposeful. In this segment, we'll explore the day-night cycle riddle, not to argue for or against a flat Earth, but to unravel its fascination. We'll journey through the interplay of observation and imagination, science and storytelling, to understand why this vision of a cycling sun and moon captivates, and what it reveals about our need for order in the cosmos. So, take a slow, deep breath, picture the sun setting or rising in your mind, and let's step into this mystery, a riddle that bends the mind and soothes the soul. Imagine yourself as a weary traveler, centuries ago, resting by a campfire under a star-filled sky. You've watched the sun rise in the east and set in the west, day after day, and you wonder, what drives this cycle? Is the sun a divine flame, circling the world to bring light and warmth? Or is the earth itself turning, as some philosophers whisper? This question, this curiosity about the rhythm of day and night, has echoed through human history, shaping myths, religions, and scientific discoveries. In flat earth theories, it takes on a new form, a vision of a sun and moon dancing above a flat plane, their paths creating the pulse of our days. As we delve into this enigma, we'll ask, how does a flat Earth explain the cycle of light and dark? Why does this idea resonate? And what does it reveal about our place in the universe? In flat Earth cosmology, the day-night cycle is explained by the motion of the sun and moon as small, local objects circling above a flat, disk-like Earth. The Earth, in this model, is a plane with the North Pole at its center, the continents radiating outward, and an icy barrier, often called the ice wall, marking its edge. The sun and moon, rather than being distant celestial bodies, a star 149.6 million kilometers away and a satellite 384,000 kilometers away, are envisioned as compact light sources, perhaps a few miles across, suspended a few thousand miles above the Earth's surface. These objects move in circular or spiral paths around the North Pole, illuminating specific regions like spotlights on a stage. When the sun's light shines over your part of the plane, it's day. When it moves away, casting its beam elsewhere, your region falls into night. To make this vivid, picture the Earth as a vast, flat table, its surface dotted with cities, forests, and oceans. Above this table, a bright lamp, the sun, moves in a circular path, its light confined to a certain radius, like a spotlight in a theater. As the lamp passes overhead, it bathes your area in daylight, warming the ground and casting shadows. As it circles away toward another part of the table, darkness falls, and the moon's softer light might take over, creating night. The sun's path, flat Earth proponents argue, is tighter or wider depending on the season, bringing it closer to the North Pole in summer, longer days, or farther out in winter, shorter days. The moon follows a similar path, its glow marking the night. Its phase is a result of its own cycle or a mechanism within the dome-like firmament that some models include. This contrasts sharply with the scientific explanation of the day-night cycle. In a mainstream model, the Earth is a spherical planet, 12,742 kilometers in diameter, rotating on its axis once every 24 hours. This rotation causes different parts of the globe to face the sun, creating day, or turn away, creating night. The sun, a massive star 1.4 million kilometers across, is 149.6 million kilometers, 93 million miles, away, its light illuminating half the Earth at any given time. The Earth's axial tilt of 23.5 degrees, combined with its annual orbit around the sun, produces the seasons, with varying daylight hours depending on latitude. This model explains a wide range of observations: the gradual progression of sunrise and sunset, the consistent timing of time zones, the geometry of solar and lunar eclipses, and the Coriolis effect, which influences weather patterns due to the Earth's rotation. The flat Earth model, however, faces significant challenges in explaining these phenomena. If the sun is a local spotlight, why doesn't its light illuminate the entire flat plane? A spotlight's beam spreads outward, and even at a few thousand miles above the Earth, the sun's light should be visible across vast distances, especially in a flat, unobstructed world. Flat Earth proponents might argue that the sun's light is constrained by atmospheric effects, a dome, or an unknown mechanism that limits its reach. But this raises further questions. Why does the sun's light fade gradually at sunrise and sunset, rather than switching off abruptly, as a spotlight might? Why does the sun maintain a consistent apparent size and brightness throughout the day, rather than appearing larger when closer and smaller when farther, as a local object would? The scientific model, with its distant sun and rotating Earth, accounts for these observations with precision, while the flat Earth model requires additional assumptions to bridge the gaps. Time zones pose another hurdle. On a spherical Earth, time zones arise because the planet's rotation exposes different longitudes to sunlight at different times, creating a 24-hour cycle across 360 degrees. When it's noon in London, it's 7 a.m. in New York and 8 p.m. in Tokyo, a pattern that aligns with the Earth's curvature. In the flat Earth model, the sun's spotlight would need to illuminate specific regions while leaving others in darkness, but this doesn't explain the smooth, predictable progression of time zones. For example, how does the sun's light reach Japan while leaving Australia in darkness, when both are on the same flat plane? The model also struggles with polar regions, where the sun remains visible for 6 months during the polar day and absent for 6 months during the polar night, a phenomenon easily explained by the Earth's tilt and rotation, but difficult to reconcile with a circling sun above a flat plane. Historically, the day-night cycle was a key factor in the shift from geocentric to heliocentric models. Ancient cultures, like the Egyptians and Babylonians, often imagined a flat Earth with the sun moving above it, carried by gods or mechanisms. By the 6th century BCE, Greek philosophers like Pythagoras proposed a spherical Earth, noting that the sun's path and the changing constellations suggested a globe. In the 3rd century BCE, Aristarchus of Samos suggested a heliocentric model, with the Earth orbiting the sun, though it was Ptolemy's geocentric model, with the sun circling a stationary Earth, that dominated until the 16th century. Copernicus's heliocentric model, refined by Kepler and Galileo, explained the day-night cycle as a result of Earth's rotation, a theory confirmed by observations like the Foucault pendulum and satellite imagery. The flat Earth day-night cycle revives pre-Copernican ideas, reimagining the sun's motion in a way that feels intuitive but struggles against modern evidence. Let's deepen this with an analogy. Imagine you're in a darkened room, and a small lamp moves in a circle above a flat table, casting a pool of light on its surface. As the lamp passes over one area, it's day. As it moves away, that area falls into night. This is the flat Earth sun, a local light creating day and night through motion. Now, contrast this with the scientific view. You're on a spinning globe, lit by a distant, massive lamp that never moves. The light seems to shift because you're turning, not because the lamp is circling. The table analogy captures the flat Earth model simplicity, but it can't explain why the lamp's light doesn't spread across the entire table, why time zones align with a curved Earth, or why the sun's path matches a rotating globe. The day-night cycle riddle is a clash of perspectives, a tension between the immediate and the universal. Flat Earth proponents, however, argue that the scientific model relies on unprovable assumptions, like the Earth's rotation or the sun's distance. They point to the sun's apparent motion, its daily arc across the sky, as evidence of a local, circling light, and claim that time zones or polar phenomena can be explained by adjusting the sun's path or atmospheric effects. Science counters with rigorous evidence. The Earth's rotation is measurable, as seen in the Coriolis effect and GPS systems, which rely on a spherical model. Telescopes reveal the sun's surface with sunspots and flares, consistent with a massive star, not a small lamp. Spacecraft, like NASA's Solar Dynamics Observatory, monitor the sun from millions of kilometers away, confirming its distance and scale. The flat Earth model, while evocative, requires dismissing these observations or invoking complex mechanisms to explain what the scientific model handles with elegance. The day-night cycle riddle is more than a cosmological puzzle. It's a profound challenge to how we explain the rhythms that govern our lives. If the sun's light is limited, confined to a spotlight-like beam above a flat plane, what does that say about the scale and structure of our world? This question invites us to reconsider the cosmos, not just its shape, but its purpose and design. The flat Earth model, with its circling sun and moon, suggests a contained, intimate universe, with a cycle of day and night is a deliberate mechanism, crafted to mark the passage of time for humanity. It's a vision that feels deeply personal, as if the heavens were set in motion just for us. But it clashes with the scientific universe, where the day-night cycle is a byproduct of a spinning planet in a vast, indifferent cosmos. The tension between these perspectives, between a purposeful stage and an impersonal expanse, raises questions about order, meaning, and our place in the universe. Let's linger on the idea of scale. In the flat Earth model, the sun is small and close, perhaps a few miles across and a few thousand miles above the Earth. This shrinks the cosmos to a human scale, making it feel knowable, like a room lit by a familiar lamp. The scientific sun, by contrast, is immense, 1.4 million kilometers in diameter, so distant that its light takes 8 minutes to reach us. This scale places us in a universe of staggering vastness, where Earth is a tiny speck among billions of stars. The flat Earth day-night cycle feels comforting because it keeps the cosmos close, manageable, a system designed with us in mind. The scientific cycle, while awe-inspiring, can evoke a sense of insignificance, a reminder that our days and nights are incidental to the universe's grand machinery. Which vision resonates more? Does the rhythm of day and night feel like a cosmic gift or a mechanical process? This question touches on philosophy, particularly the debate over teleology, the study of purpose and design. The flat Earth model is teleological, suggesting that the day-night cycle exists for a reason, perhaps to structure human life or reflect a divine plan. Ancient cosmologies, like those of the Hebrews or Greeks, often saw the sun's motion as purposeful, a sign of order in a created world. The scientific model, however, is mechanistic, viewing the cycle as a consequence of physical laws, gravity, rotation, orbital dynamics, that operate without intent. The flat Earth day-night cycle revives this sense of purpose, but it requires dismissing evidence that supports a mechanistic view, from satellite imagery to the precise timing of eclipses. What does it mean to seek purpose in a cycle that might be accidental? What does it mean to find meaning in the rhythm of light and dark, whether it's a spotlight or a star? The riddle also raises epistemological questions about how we explain natural phenomena. The flat Earth model prioritizes intuition, arguing that the sun's apparent motion, its arc across the sky, suggests a local, circling light. This aligns with pre-modern observations, when the Earth felt stationary and the heavens seemed to move. Science, however, relies on evidence beyond intuition. The Earth's rotation is measurable, its curvature visible from space, its time zones consistent with a globe. The flat Earth model asks us to trust our senses over instruments, our immediate experience over abstract data. This tension mirrors the 17th century debate between Galileo and the Church, when a heliocentric model challenged the geocentric worldview. The day-night cycle riddle is a modern echo of that struggle, asking whether we trust the lamp we see or the calculations that reveal a spinning globe. Psychologically, the flat Earth day-night cycle taps into our need for predictability and order. The rhythm of day and night is a constant, a heartbeat that structures our lives. To imagine it as a local sun circling above us is to feel anchored, part of a system that's reliable and intentional. The scientific model, with its vast distances and impersonal laws, can evoke existential unease, a sense of being adrift in a cosmos that doesn't care. The flat Earth model counters this with intimacy, but it raises a question: are we drawn to this vision because it's true, or because it soothes our fears? Are we seeing the cycle as it is, or as we wish it to be? Let's explore this through a historical lens. In the Middle Ages, the Ptolemaic model placed Earth at the universe's center, with the sun and stars orbiting in complex paths. This model aligned with observation and theology, offering a cosmos where day and night were divinely ordained. Copernicus's heliocentric model, published in 1543, upended this, explaining the day-night cycle as Earth's rotation, a theory confirmed by later discoveries like the telescope and space exploration. The flat Earth day-night cycle revives Ptolemy's vision, but it struggles against evidence like the Earth's shadow on the moon during a lunar eclipse, which reveals a curved planet. The riddle is a reminder that scientific progress often challenges our instincts, pushing us to rethink the rhythms we take for granted. Let's pause here, as the video's meditative tone invites reflection. Close your eyes, if you like, and picture the last sunrise or sunset you saw. Maybe it was a golden dawn over a quiet field, or a fiery dusk behind a city skyline. Feel the rhythm of that moment, the shift from light to dark or dark to light. What does the cycle of day and night mean to you? Not just as a physical event, but as a presence in your life. Does it feel like a cosmic clock ticking for you, or a universal process indifferent to your existence? As you listen, perhaps in the dim light of evening, let this question settle into your thoughts, a gentle pulse in the darkness. The day-night cycle riddle is not just a puzzle. It's a mirror, reflecting our need for order, our search for meaning, and our place in the rhythm of the cosmos. The implications of this riddle extend beyond astronomy into the realm of human experience. The cycle of day and night shapes how we live, how we dream, how we understand time itself. The flat Earth model offers a contained, purposeful system, but it challenges the evidence that places us in a larger, more complex universe. It's a call to balance intuition with reason, to honor both the rhythms we feel and the truths we discover. As you drift towards sleep, let the day-night cycle riddle be a quiet invitation, a chance to ponder the light and dark that define your world. As we rest in the rhythm of the day-night cycle, our minds filled with questions about the sun's path and the order of our cosmos, let's turn to another flat Earth claim that pushes the boundaries of belief. If the Earth is a flat plane, what does that mean for the stories of space exploration? How do flat Earth theories challenge the reality of satellites, moon landings, and the stars beyond? Let's explore a cosmic controversy that questions the very frontiers of human achievement. Step outside on a clear night and look up. The sky is a tapestry of stars, each a distant sun, some circled by planets we've only begun to explore. We're told that humans have walked on the moon, sent probes to Mars, and captured images of galaxies billions of light years away. These stories of astronauts floating in space, rovers rolling across alien deserts, and telescopes peering into the cosmic past are among humanity's greatest triumphs, a testament to our curiosity and ingenuity. But what if none of it is true? What if the moon landings, satellites, and space agencies like NASA are part of an elaborate deception, a grand hoax designed to convince us of a spherical Earth spinning through a vast universe? In flat Earth cosmology, this is the space hoax hypothesis, a claim that challenges the very foundations of modern science and exploration. The idea that space exploration is a lie is both shocking and strangely compelling. It suggests that the images of Earth from space, the grainy footage of Neil Armstrong's giant leap, and the data streaming from distant probes are all fabricated, staged like a Hollywood production to uphold a false cosmology. Why does this hypothesis resonate with some, even in the face of overwhelming evidence? Why does the notion of a space hoax feel like a secret whispered in the dark, a truth hidden behind a curtain of stars? In this segment, we'll explore the space hoax hypothesis, not to affirm or debunk it, but to unravel its allure. We'll weave through the threads of skepticism, trust, and human ambition, asking what this idea reveals about our relationship with the cosmos and the institutions that narrate it. So, take a slow, deep breath, let the starry sky fill your mind, and let's dive into this mystery, a cosmic controversy that questions the frontiers of human achievement. Picture yourself as a dreamer in the 1960s, glued to a black and white television as Apollo 11 touches down on the moon. The world holds its breath as astronauts take their first steps, their voices crackling through the void. It feels like a miracle, a moment when humanity transcends its earthly bounds. Now, imagine a voice in the back of your mind, whispering, what if it's all a lie? What if the moon is unreachable, the stars untouchable, and the stories of space are a carefully crafted illusion? This whisper, this seed of doubt, is the heart of the space hoax hypothesis. It's a story that taps into our deepest fears of manipulation and our yearning to uncover hidden truths. As we explore this enigma, we'll ask, why do some believe space is a hoax? How does this idea challenge our trust in science? And what does it reveal about our place in the universe? In flat Earth cosmology, the space hoax hypothesis posits that space exploration, as presented by agencies like NASA, is a grand deception orchestrated to perpetuate the idea of a spherical Earth orbiting the sun in a vast universe. Instead of a globe, flat Earth proponents envision a flat plane, often covered by a dome-like firmament, with the sun, moon, and stars as local or projected objects. To maintain this worldview, they argue, space agencies fabricate evidence of space travel, including moon landings, satellite imagery, and interplanetary missions. The Apollo program, which sent 12 astronauts to the moon between 1969 and 1972, is a frequent target, with claims that its footage was staged in a studio, possibly in Area 51 or a similar facility. Satellites, which enable GPS, weather forecasting, and global communications, are dismissed as ground-based technologies or illusions. Even images of Earth from space, showing a blue marble suspended in the void, are said to be computer-generated or manipulated. Flat Earth advocates point to several inconsistencies as evidence of a hoax. They cite the Apollo moon landing photos, claiming that shadows fall at odd angles, suggesting multiple light sources, or that the American flag appears to wave in a vacuum, which lacks wind. The Van Allen radiation belts, bands of charged particles around Earth, are said to be impassable for astronauts, making lunar travel impossible. The absence of visible satellites in the night sky, despite thousands orbiting Earth, is another point of contention, as is the claim that NASA's budget, billions of dollars annually, funds a massive cover-up rather than genuine exploration. Some even argue that the stars themselves are projections on the firmament, not distant suns, rendering the idea of space travel absurd. To understand this, let's use an analogy. Imagine a grand theater where a play about space exploration is performed. The stage is set with props, rocky moonscapes, twinkling stars, a curved Earth glowing in the distance. Actors in spacesuits deliver lines, and clever lighting creates the illusion of weightlessness. The audience, captivated, believes they're witnessing a journey to the cosmos. This, flat Earth proponents argue, is space exploration, a stage performance, with NASA as the director, convincing the world of a spherical Earth. Now, contrast this with the scientific view. The theater is the universe itself, and space exploration is real, with astronauts, probes, and telescopes revealing a cosmos of staggering scale. The play analogy captures the space hoax hypothesis's appeal, a narrative of deception that feels plausible in an age of distrust, but it falters against the evidence of actual exploration. Scientifically, space exploration is supported by overwhelming evidence. The Apollo missions left physical artifacts on the moon, including retroreflectors that allow laser beams from Earth to measure the moon's distance with millimeter precision. Independent observatories, like those in Japan and the Soviet Union, tracked Apollo spacecraft, confirming their lunar trajectories. Moon rocks, 382 kilograms brought back by Apollo, have unique isotopic signatures distinct from Earth's, verified by geologists worldwide. Satellites, over 5,000 currently in orbit, enable GPS, which powers navigation apps, and provide real-time data for weather and communications. Telescopes, like Hubble and the James Webb Space Telescope, capture images of galaxies billions of light-years away, consistent with a vast universe. Space probes like Voyager 1 and 2 have left the solar system, sending back data for decades. These achievements, documented by multiple nations and independent researchers, form a robust web of evidence that space is real and accessible. The space hoax hypothesis, however, struggles to account for this evidence. If the moon landings were staged, how were the retroreflectors placed? Why did rival nations, like the Soviet Union, never expose the hoax during the Cold War space race? If satellites don't exist, how do GPS and global internet function, with signals traceable to specific orbital paths? Flat Earth proponents might argue that all evidence is fabricated, involving a conspiracy of thousands, scientists, engineers, astronauts, and governments, maintained without leaks for decades. This requires an extraordinary level of coordination, far beyond what historical conspiracies, like Watergate, could sustain. Science, by contrast, operates on transparency, with data open to scrutiny, from lunar rock samples to satellite telemetry. Historically, the space race was a triumph of science and human ambition. Sparked by the Soviet Union's launch of Sputnik in 1957, it drove the United States and others to push the boundaries of technology. The Apollo program, costing $25 billion, over $150 billion today, involved 400,000 workers and produced tangible results. Lunar landings, live broadcasts, and scientific data still studied today. The Soviet Union's Luna program and China's Chang'e missions have also reached the moon, while private companies like SpaceX launch satellites and plan Mars missions. These efforts, spanning nations and eras, contradict the idea of a unified hoax. Yet, Skepticism persists in flat Earth circles, fueled by distrust of institutions and a belief that the spherical Earth is a lie to obscure a flat, contained world. Let's deepen this with another analogy. Imagine you're reading a book about a fantastical journey to distant lands. The author describes vivid landscapes, but you suspect it's fiction, a tale spun to deceive. This is the flat Earth view of space exploration, a story, not reality. Now, imagine you're an explorer standing on those lands, touching their soil, measuring their skies. This is the scientific view, a lived experience backed by evidence. The book analogy highlights the space hoax hypothesis's reliance on narrative over proof, but it can't explain the tangible artifacts, moon rocks, satellite signals, cosmic images, that anchor the scientific story. The hypothesis is a tale of doubt, compelling in its simplicity, but fragile against the weight of discovery. Flat Earth proponents, however, argue that the scientific narrative relies on trust in unprovable claims, like the existence of space or the authenticity of NASA's images. They point to cultural touchstones like the 1978 film Capricorn 1, which depicted a staged Mars mission, as evidence that such hoaxes are plausible. Science counters with reproducibility. Amateur astronomers track satellites with telescopes. Ham radio operators bounce signals off the moon, and anyone can verify GPS coordinates. The space hoax hypothesis, while emotionally resonant, requires dismissing a global network of evidence, replacing it with a narrative of deception that's harder to sustain than the reality it denies. The space hoax hypothesis is more than a cosmological claim. It's a profound challenge to our faith in collective achievements and the institutions that enable them. If space exploration is a lie, what else might be fabricated? This question strikes at the heart of how we construct knowledge, trust, and reality itself. The idea that moon landings, satellites, and cosmic discoveries are staged suggests a world where truth is manipulated, where humanity's greatest feats are illusions crafted by a select few. It's a vision that taps into existential fears about control, deception, and the fragility of our understanding, yet also sparks curiosity, urging us to verify truth for ourselves. The space hoax hypothesis is both unsettling and empowering, a paradox that asks us to question everything while seeking answers in the stars. Let's linger on the erosion of trust. The space hoax hypothesis thrives in an era of skepticism, where institutions, governments, corporations, media are often viewed with suspicion. NASA, as a symbol of scientific authority, becomes a lightning rod for distrust, its budget and secrecy, classified missions during the Cold War, fueling conspiracy theories. If the moon landings were faked, it implies a conspiracy involving thousands, sustained across decades, with no definitive whistleblower. This level of distrust extends beyond space, questioning the validity of climate data, medical research, or historical records. It's a slippery slope. If we can't trust the images of Earth from space, what can we trust? Yet, this skepticism also empowers, encouraging individuals to seek evidence themselves, from tracking satellites to studying lunar rocks. The space hoax hypothesis is a double-edged sword, undermining collective achievements while igniting personal inquiry. Philosophically, the hypothesis touches on epistemology, the study of knowledge and belief. How do we know what we know? The scientific view of space relies on empirical evidence, artifacts, measurements, and reproducible experiments. The flat Earth view prioritizes intuition and skepticism, arguing that personal observation, no visible satellites, questionable photos, trumps institutional claims. This mirrors the 17th century debate between Galileo and the Church, when telescopic evidence of a heliocentric universe challenged biblical authority. The space hoax hypothesis revives this tension, asking whether we trust the tools of science, telescopes, probes, computers, or the doubts of our own eyes. It's a question that resonates in a world of fake news and competing narratives, where truth feels increasingly elusive. The hypothesis also raises existential questions about human ambition. Space exploration is a symbol of our drive to transcend limits, to touch the moon and dream of Mars. If it's a hoax, that dream collapses, leaving us confined to a flat, domed world, perhaps designed but ultimately limited. This vision is both comforting and confining. Comforting because it suggests a contained, purposeful cosmos, confining because it denies the infinite possibilities of space. The scientific view, with its vast universe, evokes all but also insignificance, a sense that we're small in a cosmos that doesn't care. The space hoax hypothesis offers a middle ground, a world where we're central, but at the cost of our exploratory legacy. What does it mean to dream of the stars if those dreams are illusions? What does it mean to be human if our greatest triumphs are lies? Let's explore this through a historical lens. The space race, sparked by Sputnik in 1957, was a battle of ideologies as much as technology. The United States and Soviet Union competed to prove their systems. Capitalism versus communism, through cosmic achievements. The moon landings, watched by 600 million people, were a unifying moment, a shared leap for humanity. The space hoax hypothesis undermines this, suggesting division and deception instead of unity. Yet, it reflects a historical pattern. Major advancements, from Copernicus's heliocentrism to Darwin's evolution, have faced skepticism, often rooted in fear of upending established truths. The space hoax hypothesis is a modern echo, a resistance to a universe that disintermediates humanity, replacing it with a narrative of control and concealment. Psychologically, the hypothesis taps into our fear of manipulation and our desire for autonomy. Believing in a space hoax empowers the individual, positioning them as a truth seeker against a deceptive system. It's a narrative of rebellion, appealing in an age where information is abundant but trust is scarce. But it also isolates, pitting personal belief against collective evidence. The scientific view, with its open data, lunar samples, satellite feeds, mission logs, invites participation, while the hoax narrative demands faith in an alternative story. The space hoax hypothesis is a choice between community and solitude, between trusting humanity's shared journey or seeking truth alone. Let's pause here, as the video's meditative tone invites reflection. Picture the night sky, its stars twinkling above you. Maybe you've seen a satellite pass, a steady dot moving among the constellations, or watch a rocket launch on TV. Now, imagine those are illusions, part of grand play. What do you feel when you look at the stars? Do you trust the stories we're told about them? Astronauts, probes, distant worlds, or does a whisper of doubt linger? As you listen, perhaps in the quiet of your room, let this question settle into your thoughts, a soft glow in the darkness. The space hoax hypothesis is not just a claim. It's a mirror, reflecting our fears, our hopes, and our endless quest for truth. The implications of this hypothesis extend beyond cosmology into the realm of human experience. It challenges us to define what we believe and why, to balance skepticism with trust, to honor both our doubts and our discoveries. The space hoax hypothesis is a call to question, but also to seek, to look at the stars and decide for ourselves what they mean. As you drift towards sleep, let this enigma be a gentle nudge, a chance to ponder the stories that light the night. As we rest beneath the questioned stars, our minds swirling with doubts about space and the truths we hold, let's turn to another flat Earth mystery. If the Earth is a flat plane, how does it generate the magnetic field that guides our compasses and shapes the poles? What forces align the needle toward north? Let's dive into a magnetic mystery that pulls us deeper into the enigma of a flat Earth. Hold a compass in your hand, its needle quivering, then settling, pointing steadfastly north. For centuries, this simple tool has guided explorers across storm-tossed seas, through trackless deserts, and over snow-clad mountains. It's a quiet marvel, a whisper of the Earth's invisible forces, always directing us toward a fixed point, the North Pole. On a spherical Earth, this behavior is explained by the planet's magnetic field, a dynamic force generated deep within its core, aligning compasses and painting the skies with auroras. But what if the Earth isn't a globe? What if it's a flat plane, stretching out beneath a dome or an open sky? How, then, does a compass needle find its way? How does magnetism work in a world without a South Pole, as we know it? In flat Earth cosmology, this is the polar magnetism puzzle, a concept that defies logic and challenges our understanding of navigation and orientation. The idea of a flat Earth with a central North Pole and no true South Pole is both intriguing and perplexing. It reimagines the magnetic field as a radial force emanating from a single point, with the southern regions often described as an encircling ice wall, serving as a kind of magnetic periphery. This vision feels ancient, almost mythical, evoking a world where the center holds everything together, a cosmic hub around which all else revolves. Yet, it raises questions that tug at the edges of reason. Why does a compass work consistently across the globe? Why do auroras dance at both poles? In this segment, we'll explore the polar magnetism puzzle, not to affirm or refute the flat Earth model, but to unravel its allure. We'll weave through the interplay of science and intuition, history and philosophy, to understand why this idea captivates and what it reveals about our need for direction in an uncertain world. So, take a slow, deep breath, imagine a compass needle spinning in your palm, and let's step into this mystery, a puzzle that points us toward the heart of the Earth. Picture yourself as a medieval sailor, standing at the helm of a creaking ship under a starlit sky. Your only guide is a lodestone, a magnetic rock that pulls toward the north, steering you through the dark. You trust it implicitly, as your ancestors did, believing it connects you to the center of the world. Now, imagine a flat Earth theorist today holding a modern compass, claiming that north is the center of a flat plane and south is not a point but a boundary. This vision, this reimagination of magnetism, taps into the same instinct that guided that sailor, the need for a fixed point, a reference that anchors us. As we delve into this enigma, we'll ask, how does a flat Earth explain the compass's reliability? Why does the polar magnetism puzzle resonate? And what does it reveal about our search for direction, both physical and metaphysical? In flat Earth cosmology, the Earth is envisioned as a flat, circular plane with a North Pole at its center, the continents radiating outward, and an outer boundary, often called the Ice Wall or Antarctic Rim, encircling the whole. The magnetic field, in this model, is reimagined to fit this geometry. The North Pole is the magnetic hub, a central point from which magnetic field lines radiate outward across the plane, like spokes from the hub of a wheel. A compass needle, attracted to this central magnetic source, always points toward the North Pole, no matter where you stand on the plane. The South Pole, rather than being a distinct magnetic point as in the scientific model, is conceptualized as the outer edge of the plane, where magnetic field lines might converge or dissipate. Some flat Earth proponents suggest that the ice wall itself has magnetic properties, or that the magnetic field weakens as it extends outward, creating the illusion of a southern magnetic pole. To visualize this, imagine the Earth as a vast, flat table with a powerful magnet placed at its center, the North Pole. The magnet's field spreads outward in all directions, pulling compass needles toward the center from every point on the table. At the table's edge, the field might curve or fade, but there's no single South Pole as a mirror image of the North. Instead, the edge itself, the ice wall, serves as a kind of magnetic boundary. This model explains why compasses point north, flat Earth advocates argue, without needing a spherical Earth or a molten core. They might claim that the consistency of compass readings worldwide supports a central North Pole, and that the absence of a clear South Pole in their model aligns with restricted access to Antarctica, which they view as a guarded perimeter rather than a continent. In scientific terms, the Earth's magnetic field is generated by the dynamo effect in its molten outer core, where swirling currents of liquid iron and nickel create a magnetic dipole, a field with a north and south magnetic pole. These poles are not fixed. They wander slightly and have even reverse polarity multiple times over millions of years, as recorded in volcanic rocks. The magnetic North Pole is currently near the geographic North Pole, and the magnetic south pole is near the geographic south pole, though both are offset due to the field's complexity. Compasses align with the field lines, pointing toward the magnetic north pole, and work consistently worldwide because the field envelopes the spherical Earth. This model explains phenomena like the aurora borealis, northern lights, and aurora australis, southern lights, where charged particles from the sun interact with the magnetic field at both poles, creating dazzling displays. The flat Earth model, however, struggles to account for these observations. If the North Pole is the sole magnetic center, why do compasses in the southern hemisphere, say in Australia or Argentina, point north without requiring a southern magnetic point to balance the field? The scientific model's dipole field naturally explains this. Field lines curve from the North Pole to the South Pole, guiding needles globally. In the flat Earth model, the radial field would need to maintain consistent strength and direction across vast distances, which is physically implausible without a corresponding southern pole. Moreover, the auroras pose a problem. Why do they appear symmetrically at both poles, with similar patterns of frequencies, if the South Pole is merely an edge? The scientific model attributes this to the field's symmetry, while the flat Earth model requires additional mechanisms, like atmospheric effects or a dome, to explain the southern lights. Another challenge is navigation. Explorers like Roald Amundsen, who reached the South Pole in 1911, used compasses to navigate Antarctica, finding a distinct magnetic South Pole. Modern GPS and magnetic surveys confirm the pole's location, shifting slightly over time. In the flat Earth model, navigating the ice wall should reveal a diffuse or inconsistent magnetic field, not a focus pole. Satellite data, such as from the European Space Agency's SWARM mission, map the Earth's magnetic field in detail, showing a dipole structure inconsistent with a flat plane. Flat Earth proponents might dismiss satellites as part of the space hoax, but this doesn't explain ground-based magnetic measurements, like those from observatories in Antarctica, which align with a spherical Earth. Let's explore this with an analogy. Imagine a flat table with a magnet placed at its center, pulling metal filings toward it in a radial pattern. This is the flat Earth magnetic field, a central North Pole drawing compasses inward. Now, picture a spherical magnet, like a globe, with field lines looping from one pole to the other, guiding filings in a curved path. This is the scientific field, a dipole with north and south poles. The table analogy captures the flat Earth model simplicity, but it can't explain why filings, compasses, behave consistently far from the center, why auroras light up both ends, or why magnetic data match a sphere. The scientific model, while more complex, accounts for these phenomena with precision, from compass readings to polar lights. Historically, magnetism played a crucial role in confirming Earth's sphericity. In the 16th century, William Gilbert, an English physician, proposed that Earth was a giant magnet, explaining why compasses worked globally. His work, De Magnete, 1600, laid the groundwork for understanding the magnetic field, supporting a spherical Earth. By the 19th century, explorers like James Clark Ross mapped the magnetic poles, finding both a north and south, consistent with the globe. Modern science, using seismology and satellite data, has traced the field's origins to the core, reinforcing the spherical model. Flat Earth theories, however, reimagine magnetism to fit a flat plane, reviving pre-modern ideas where the North Pole was the world's center and South was an undefined edge. Flat Earth proponents argue that the scientific model relies on unprovable assumptions, like a molten core or satellites, and that compass behavior supports a central North Pole. They might claim that auroras are atmospheric phenomena, not tied to a southern pole, or that Antarctic data is fabricated to hide the ice wall. Science counters with reproducible evidence. Magnetometers measure the field's strength and direction worldwide. Auroras are photographed at both poles, and core samples from Antarctica align with the dipole field. The polar magnetism puzzle, while intuitive in its simplicity, bends under the weight of global observations, requiring complex explanations where science offers clarity. The polar magnetism puzzle is more than a debate about compasses and poles. It's a profound challenge to how we navigate the world, both physically and philosophically. If the Earth's magnetic field is misunderstood, if the North Pole is a center and the South Pole a myth, how do we find our way? This question strikes at the heart of orientation, not just on maps, but in our understanding of reality. The flat Earth model, with its central North Pole and radial magnetism, offers a cosmos that feels anchored, where a single point provides direction for all. It's a vision that resonates with our need for a center, a reference that holds the world together. But it clashes with the scientific universe, where magnetism is a dynamic force, linking two poles in a spherical dance. The tension between these perspectives, between a centered plane and a balanced globe, raises questions about guidance, trust, and our place in the cosmos. Let's linger on the idea of navigation. A compass is more than a tool. It's a symbol of reliability, a promise that we can find our way, no matter how lost we feel. In the flat Earth model, the compass's unwavering point to the North Pole suggests a world designed with clarity, where direction is universal and the center is always accessible. This is comforting, especially in moments of uncertainty, when the world feels chaotic and we crave a fixed point to guide us. The scientific model, with its dipole field, is less intuitive but more versatile, explaining why compasses work from the Arctic to Antarctica, why ships sail true, and why auroras light up both skies. If the flat Earth model is wrong, it challenges the compass's simplicity, forcing us to rely on complex systems, GPS, satellites, geomagnetic data, to navigate. What does it mean to trust a needle that points north, only to question the world it points toward? What does it mean to find direction in a cosmos that might not have a center? This question touches on philosophy, particularly the concept of orientation in existential terms. The 20th century philosopher Martin Heidegger described being in the world as a state of orientation, where we seek meaning and direction in our existence. The flat Earth model offers a literal center, the North Pole, as a metaphor for this, a point that grounds us in a finite, purposeful world. The scientific model, with its dual poles and vast universe, suggests a more fluid orientation, where direction is relative and meaning is constructed, not given. The polar magnetism puzzle asks, do we need a single center to feel grounded, or can we navigate a world of multiple poles, of shifting fields and endless horizons? It's a question that resonates beyond magnetism, touching on how we find purpose in our lives, how we chart a course through uncertainty. The puzzle also raises epistemological questions about evidence and intuition. The flat Earth model prioritizes the compass's apparent simplicity, arguing that its northward pole supports a central pole on a flat plane. This aligns with pre-modern navigation, when sailors trusted lodestones without understanding magnetism's mechanics. Science, however, demands evidence beyond intuition. Magnetometers map the field's curvature, auroras reveal its symmetry, and core samples trace its history. The flat Earth model asks us to trust our senses over instruments, our immediate experience over global data. This tension echoes the 19th century debates over Earth's shape, when magnetic surveys helped confirm a globe, challenging flat cosmologies. The polar magnetism puzzle is a modern echo, asking whether we trust the needle or the numbers, the center or the sphere. Psychologically, the flat Earth model taps into our need for stability. A central North Pole, with magnetism radiating outward, feels like an anchor, a point that never wavers. The scientific model, with its wandering poles and dynamic core, can evoke unease, a sense that even the Earth's field is in flux. The flat Earth model counters this with certainty, but it raises a question: are we drawn to this vision because it's true, or because it soothes our fears? Are we seeing the magnetic field as it is, or as we wish it to be? This question mirrors our broader search for guidance, whether in science, spirituality, or personal belief, where we seek a North Star to steer by, even when the world feels unmoored. Let's explore this through a historical lens. In the age of sail, compasses were revolutionary, enabling global exploration and trade. By the 19th century, scientists like Carl Friedrich Gauss developed mathematical models of the magnetic field, confirming its dipole nature and supporting a spherical Earth. The discovery of magnetic pole reversals, recorded in ancient rocks, added depth to this model, revealing a planet with a dynamic history. The flat Earth model revives older visions, like those of medieval cartographers who placed Jerusalem or the North Pole at the world's center, with South as a vague periphery. The polar magnetism puzzle is a clash of eras, pitting modern evidence against ancient intuition, asking whether we navigate by the past or the present. The implications of this puzzle extend to our cultural narratives. The compass is a universal symbol, appearing in literature, art, and mythology as a guide through chaos. In Dante's Divine Comedy, the journey through hell and purgatory is a quest for orientation, a search for divine direction. The flat Earth model, with its central pole, aligns with this archetype, offering a world where guidance is clear and absolute. The scientific model, with its complex field, challenges this simplicity, suggesting a world where direction is relative and guidance requires effort. The polar magnetism puzzle asks us to choose between a mythic center and a scientific spectrum, between a world that holds us close and one that sets us free. Let's pause here, as the video's meditative tone invites reflection. Picture a compass in your hand, its needle steady, pointing north. Feel the weight of it, the quiet assurance of direction. Now, imagine you're lost, not on a map, but in life. What guides you? Is it a single point, a north star of belief or purpose, or a network of signs, shifting and complex? As you listen, perhaps in the stillness of your room, let this question linger, a gentle pull in your thoughts. The polar magnetism puzzle is not just a mystery. It's a mirror, reflecting our need for direction, our trust in the tools we use, and our endless search for a center in an uncertain world. The polar magnetism puzzle is a call to balance simplicity and complexity, intuition and evidence. It challenges us to navigate not just the Earth, but our beliefs, our doubts, and our dreams. As you drift towards sleep, let this enigma be a quiet invitation, a chance to ponder what guides you when the way is unclear, what points you north when the world feels flat or round. As we rest in the pull of the polar magnetism puzzle, our minds swirling with questions about compasses, poles, and the forces that guide us, let's turn to another flat Earth mystery. If the Earth is a flat plane, how do its continents take shape? Why do maps in these models look so different from the ones we know? Let's explore a cartographic conundrum that redraws the world, drawing us deeper into the enigma of a flat Earth. Spread a map across a table, its lines and colors tracing the contours of continents, oceans, and borders. It's a window to the world, a guide that tells you where mountains rise, where rivers flow, and where one nation meets another. For centuries, maps have been our companions, helping us navigate, dream, and understand our place on Earth. But what if the map you're holding is lying? What if the familiar shapes of continents, Africa's broad curve, Australia's rugged outline, are stretched, warped, or misplaced to fit a vision of the world that defies what we've been taught? In flat Earth cosmology, maps are not just tools, they're battlegrounds, where the shape of the Earth itself is contested. The azimuthal equidistant projection, a map favored by many flat Earth proponents, places the North Pole at the center and stretches the continents outward, with Antarctica as a vast, encircling ice wall. These maps feel alien, almost otherworldly, their distortions challenging our sense of geography and reality. Why do flat Earth maps look so strange, so unlike the Mercator or globe-based maps we know? Why do they evoke a mix of fascination and unease, as if the world we thought we understood has been redrawn? The Distorted Map Conundrum is not just about cartography. It's about perception, trust, and the stories we tell about the world. It asks us to question the tools we use to orient ourselves and the truths they claim to represent. In this segment, we'll explore the Distorted Map Conundrum, not to argue for or against a flat Earth, but to unravel its allure. We'll journey through the interplay of science and imagination, history and philosophy, to understand why these maps captivate and what they reveal about our need to see the world clearly. So, take a slow, deep breath, picture a map unfurling before you, and let's step into this mystery, a conundrum that reshapes the Earth in our minds. Imagine yourself as a cartographer in a candlelit study, centuries ago, hunched over a parchment, sketching the world as you know it. Your sources are sailors' tales, ancient texts, and your own intuition, and you place the known lands at the center with the edges fading into mystery. Now, picture a modern flat Earth enthusiast holding a map that echoes your work, a flat plane with the North Pole at its heart, the continents splayed outward and the edges guarded by ice. This map, like yours, is a story, a vision of the world that feels true to its creator. As we delve into this enigma, we'll ask, why do flat Earth maps distort the world so dramatically? How do they challenge our trust in geography? And what do they reveal about our longing for a world that makes sense? In flat Earth cosmology, the Earth is envisioned as a flat, circular plane, with the North Pole at its center, the continents radiating outward like petals, and Antarctica reimagined as a massive ice wall or rim encircling the entire plane. To represent this model, flat Earth proponents often use the azimuthal equidistant projection, a map that places the North Pole at the center and stretches the continents outward in a radial pattern. On this map, the Northern Hemisphere appears relatively undistorted, with North America, Europe, and Asia fanning out from the central pole. The Southern Hemisphere, however, is dramatically warped. Australia and South America appear elongated. Antarctica becomes a sprawling, circular barrier, and distances between southern continents are exaggerated. This map is not just a depiction of geography. It's a declaration of a flat, contained world, where the North Pole is the hub and the ice wall the boundary. To understand this, let's visualize the flat Earth map. Picture a round table, with a pin at its center marking the North Pole. Around this pin, you place cutouts of the continents, arranging them as they appear in the Northern Hemisphere, Canada and Russia close to the center, Europe and Asia a bit farther out. As you move toward the table's edge, the Southern Hemisphere continents, like Australia and South Africa, are stretched and pulled apart, their shapes distorted to fit the circular plane. At the table's rim, you draw a thick band of ice, Antarctica, encircling everything, holding the oceans in place. This is the azimuthal equidistant projection, a map that prioritizes the North Pole's centrality and the flat Earth's bounded nature. Flat Earth proponents argue that this map reflects the true shape of the world, undistorted by the assumptions of a spherical Earth, and that its layout explains phenomena like flight paths or the apparent size of southern continents. In scientific terms, maps are projections, attempts to represent the three-dimensional surface of a spherical Earth on a two-dimensional plane. Because a sphere cannot be flattened without distortion, every map projection involves trade-offs, prioritizing certain features, like shape, area, or distance, at the expense of others. The Mercator projection, familiar from many world maps, preserves shapes but inflates areas near the poles, making Greenland appear as large as Africa, though it's 14 times smaller. The azimuthal equidistant projection, used in polar maps and by flat Earth advocates, preserves distances from the North Pole but distorts shapes and areas in the Southern Hemisphere, stretching Australia and Antarctica unnaturally. Globe-based maps, derived from satellite imagery and GPS, reflect the Earth's true curvature, with continents and oceans proportioned accurately, as confirmed by measurements like ship voyages and airline routes. The flat Earth map, however, struggles to align with these observations. If the Earth is a flat plane, why do southern continents appear so distorted on the azimuthal map? Australia, for example, is stretched to appear much larger than it is, and the distance between South America and Africa is exaggerated, contradicting real-world measurements. Airline routes in the Southern Hemisphere, like Sydney to Santiago, are shorter than the flat Earth map suggests, matching a spherical Earth geometry. The azimuthal map also fails to explain why ships can circumnavigate Antarctica in about 24,000 kilometers, consistent with a continent, not an endless ice wall. Flat Earth proponents might argue that these discrepancies are due to navigational errors or conspiracies, claiming that maps like the Mercator are designed to obscure the flat Earth's true shape. Let's explore this with an analogy. Imagine peeling an orange and trying to flatten its skin onto a table. No matter how you press or cut, the skin tears or stretches, distorting the orange's surface. This is the challenge of map making. A spherical Earth cannot be perfectly flattened, so every map is a compromise. The flat Earth map is like choosing one piece of the peel, the North Pole, and stretching the rest around it, warping the southern regions to fit a flat plane. The scientific map, by contrast, starts with the whole orange, using math and measurements to minimize distortion, as seen in globe-based projections. The orange analogy captures the flat Earth map's intuitive appeal. A centered, simplified world, but it can't explain why the peel's edges, the southern hemisphere, are so misshapen, or why real-world distances match a sphere. Historically, map-making evolved alongside our understanding of Earth's shape. Ancient maps, like the Babylonian world map, 6th century BCE, depicted a flat Earth with a central landmass and surrounding ocean. Medieval TO maps placed Jerusalem at the center, with continents radiating outward, reflecting a theological rather than empirical view. By the 16th century, explorers like Ferdinand Magellan and cartographers like Gerardus Mercator confirmed Earth's sphericity, developing projections that accounted for its curvature. The 20th century brought satellite imagery, enabling precise maps that align with the globe. Flat Earth maps, like the azimuthal equidistant projection, revive older cosmologies, prioritizing a central North Pole and a bounded world, but they struggle against modern evidence, from GPS coordinates to oceanic voyages. Flat Earth proponents argue that globe-based maps are part of a deception designed to uphold a spherical Earth narrative. They claim the azimuthal map better reflects reality, citing its use in polar maps or UN logos as evidence of its truth. Science counters with reproducibility. Surveyors measure distances, pilots fly routes, and satellites map the Earth, all consistent with the globe. The distorted map conundrum, while evocative, requires dismissing these measurements or invoking conspiracies to explain why the azimuthal map's distortions don't match real-world geography. The scientific model, with its array of projections, acknowledges distortion as a necessary trade-off, offering maps that balance accuracy with utility. Let's deepen this with another analogy. Imagine the Earth as a quilt, its patches representing continents. On a globe, the quilt wraps snugly, each patch in proportion. On a flat Earth map, you spread the quilt flat, pulling the center, the North Pole, tight, but the edges fray, stretching the southern patches out of shape. This is the azimuthal projection, a centered map that sacrifices southern accuracy for northern clarity. The scientific quilt, while complex, fits the Earth's curves, as seen in satellite images and nautical charts. The quilt analogy highlights the flat Earth map's appeal, a tidy, centered world, but it can't explain why the southern patches are so warped or why real-world measurements align with the globe. The distorted map conundrum is more than a cartographic debate. It's a profound challenge to our trust in the representations we use to understand reality. If maps, the tools we rely on to navigate and comprehend the world, are flawed or deceptive, how do we know where we stand? This question shakes the foundations of our knowledge, inviting us to question not just geography, but the stories we tell about the world. The flat Earth map, with its centered North Pole and sprawling ice wall, offers a vision of a contained, purposeful Earth, where humanity occupies a central place. It's a comforting image, like a medieval map with a holy city at its heart, but its distortions stretched continents, misplaced distances, confront us with an unsettling truth. No map is perfect, and every representation is, in some way, a story. Let's linger on the erosion of trust. Maps are not just drawings. They're agreements, collective efforts to depict the world as we understand it. The Flat Earth map rejects this consensus, arguing that globe-based maps are lies, crafted to perpetuate a spherical Earth narrative. This rejection resonates in an era of skepticism, where institutions, governments, scientists, media are often questioned. If maps are deceptive, what else might be? The flat Earth map empowers the individual, suggesting that personal intuition or alternative sources can reveal a hidden truth. But it also isolates, pitting one's belief against the evidence of countless measurements, from ship logs to satellite data. The distorted map conundrum asks, do we trust the maps we're given, or do we redraw the world ourselves? It's a question that extends beyond cartography, touching on how we navigate information, authority, and truth in a complex world. Philosophically, the conundrum raises questions about perspective and representation. The 20th century philosopher Ludwig Wittgenstein argued that our understanding of the world is shaped by the pictures we hold, the frameworks that organize our perceptions. The flat Earth map is such a picture, a vision of a centered, flat world that prioritizes simplicity and human centrality. The scientific map, with its array of projections, acknowledges complexity, admitting that no single view captures the whole truth. The distorted map conundrum asks, is there a true way to see the world, or are all maps, all perspectives, inherently limited? This resonates with postmodern ideas, where reality is seen as a construct shaped by the lenses we use. The flat Earth map, with its bold distortions, challenges us to choose between a singular, comforting picture and a multifaceted, sometimes disorienting truth. The conundrum also touches on existential questions about place and identity. Maps do more than show geography. They tell us where we belong, how we relate to the world. The flat Earth map, with its central North Pole, places humanity at the heart of creation, a comforting notion in a universe that science describes as vast and indifferent. The azimuthal projections distortions, stretching Australia, warping Antarctica, reflect this priority, sacrificing accuracy for a sense of centrality. The scientific map, with its proportional continents, disintegers us, placing Earth as one planet among billions. What does it mean to live in a world without a center? What does it mean to find your place when a map you trust might be a story, not a fact? These questions echo our personal searches for belonging, for a sense of home in an ever-shifting world. Let's explore this through a historical lens. Map-making has always been a blend of science and storytelling. The maps of Ptolemy in the 2nd century CE combined Greek knowledge with myth, depicting a world with known lands and mysterious edges. The Age of Exploration, with figures like Columbus and Magellan, refined maps through empirical data, confirming Earth's sphericity. The 20th century satellite era produced maps of unprecedented accuracy. Yet even these are projections, choosing what to emphasize, area, shape, or distance, at the expense of a perfect depiction. The flat Earth map, with its azimuthal equidistant projection, harks back to those earlier eras, prioritizing a central North Pole and a bounded world over empirical precision. This revival of older cosmologies speaks to a longing for simplicity, for a time when the world felt smaller and more knowable. But it also confronts us with a challenge. If maps are stories, how do we discern which story is true? The distorted map conundrum invites us to grapple with the tension between nostalgia and discovery, between the maps that comfort us and those that reflect the world as we measure it. The implications of this conundrum extend to our cultural narratives about space and place. Maps are not neutral. They carry the biases of their creators, shaping how we see the world. The Mercator projection, developed in 1569, was designed for navigation, preserving angles for sailors but inflating polar regions, which subtly reinforced Eurocentric views by enlarging Europe and North America. The flat Earth map, with its centered North Pole and sprawling Antarctica, tells a different story, one of human centrality, where the world is a stage with a clear focal point. This narrative resonates with ancient myths, like the Norse world tree Yggdrasil at the cosmos' center, or medieval maps, placing Jerusalem as the heart of creation. Yet, its distortions, stretching southern continents, warping distances, reveal a trade-off. To prioritize a central vision, it sacrifices geographical accuracy. The scientific map, with its array of projections, strives for balance, using data from satellites and surveys to minimize bias. The conundrum asks, do we prefer a map that tells a comforting story or one that aligns with the world we can measure? This choice mirrors broader cultural debates about truth and perspective, where we weigh tradition against evidence, intuition against reason. Psychologically, the flat Earth map taps into our need for orientation and certainty. A map with a central North Pole and a defined boundary, like the ice wall, feels like a safe haven, a world where we know our place. The azimuthal projection's distortions, while jarring, reinforce this sense of containment, suggesting a cosmos designed with humanity in mind. The scientific map, with its proportional but complex projections, can evoke unease, reminding us that Earth is a small sphere in an infinite universe, with no inherent center. This contrast reflects a deeper tension. Do we seek a world that feels purposeful, where we're at the heart, or one that embraces the vastness, where our place is relative? The distorted map conundrum challenges us to confront this tension, to decide whether we value the map's story or its fidelity to reality. The conundrum also raises practical questions about navigation and exploration. Maps are tools for action, guiding ships, planes, and hikers across the globe. The flat Earth map, with its stretched southern regions, fails to explain why airline routes, like Sydney to Santiago, about 11,300 kilometers, are shorter than its layout suggests. On a spherical Earth, these routes follow great circle paths, curving over the globe for efficiency, as confirmed by flight data and GPS. The azimuthal map, however, implies vast distances in the southern hemisphere, making such routes implausible without invoking errors or conspiracies. Similarly, circumnavigations of Antarctica, completed by explorers like James Cook in the 18th century, cover roughly 24,000 kilometers, consistent with a continent, not an endless ice wall. The flat Earth map's distortions undermine its utility, forcing proponents to dismiss real-world measurements or claim that navigators are misled by false maps. The scientific map, while imperfect, supports navigation with precision, from nautical charts to satellite-guided systems. The conundrum asks, can a map guide us if its shapes betray the world we travel? Let's explore this through a philosophical lens, particularly the concept of representation versus reality. The 17th century philosopher John Locke distinguished between the real world and our ideas of it, suggesting that our perceptions are mediated by imperfect tools. Maps are such tools, translating the Earth's complexity into lines and colors. The flat Earth map represents a reality where the North Pole is central and the world is flat, a vision that feels immediate but distorts measurable geography. The scientific map represents a spherical Earth, using math and data to approximate reality. Yet too is a construct, choosing what to emphasize. The distorted map conundrum echoes Locke's insight, asking whether any map can capture the world's true essence, or if all maps are, in some way, fictions. This resonates with modern debates about reality in the digital age, where images, data, and narratives compete to define truth. The flat Earth map, with its bold distortions, challenges us to question the fictions we accept and the realities we seek. The conundrum also evokes a sense of existential disorientation. Maps anchor us, giving us a sense of where we are and where we're going. The flat Earth map, with its alien shapes, disrupts this anchor, suggesting that the world we know, Africa's curve, Australia's outline, is a lie. This disruption can be unsettling, like waking in a familiar room to find the furniture rearranged. Yet, it's also liberating, inviting us to redraw the world, to imagine new ways of seeing. The scientific map, with its familiar continents, offers stability but risks complacency, assuming we've mapped the world correctly. The distorted map conundrum asks, what happens when we lose our bearings? How do we find our place when the map we trust is called into question? These questions mirror our personal journeys, where we navigate relationships, beliefs, and goals, seeking a map that feels true, even as the world shifts beneath us. Let's deepen this with a cultural perspective. Maps have always been more than geography. They're expressions of power, belief, and identity. Colonial maps redrew borders to claim territories, often erasing indigenous perspectives. The Flat Earth map, with its centered North Pole, asserts a cosmological claim, rejecting the scientific consensus for a vision rooted in ancient and alternative worldviews. Its use in modern contexts, like the United Nations logo, is cited by proponents as evidence of its truth, though the logo's azimuthal projection is chosen for its polar clarity, not a flat Earth. The scientific map, backed by global institutions, reflects a collective effort to understand Earth, but it too carries biases, like the Mercator's Eurocentric distortions. The Distorted Map Conundrum highlights this interplay of power and perspective, asking who gets to draw the map and whose story it tells. It's a reminder that maps, like all representations, are shaped by the hands that hold the pen. The implications of the conundrum extend to our technological world. Modern maps, powered by satellites and GPS, are dynamic, updating in real time to guide us through cities and wilderness. The Flat Earth map, static and centered, rejects this technology, claiming satellites are a hoax and GPS is ground-based. This rejection challenges the infrastructure of our lives. Navigation apps, weather forecasts, global communications, all reliant on a spherical Earth model. Yet, it also sparks curiosity, urging us to question the systems we take for granted. The Distorted Map Conundrum asks, do we trust the digital maps that guide us, or do we seek a simpler, more human-centered view? This tension mirrors our broader relationship with technology, where we balance convenience with skepticism, progress with reflection. Let's pause here, as the video's meditative tone invites reflection. Picture a map of your world, not just the Earth, but your life. Maybe it's a mental map of places you've been, people you love, or dreams you chase. Does it feel accurate, with every detail in place, or like a story, with some parts stretched or blurred? What happens when you question its lines, when the world you thought you knew looks different? As you listen, perhaps in the quiet of your room, let this question linger, a soft unfolding in your thoughts. The Distorted Map Conundrum is not just a puzzle. It's a mirror, reflecting our need for clarity, our trust in the tools we use, and our endless search for a world that feels true. The Distorted Map Conundrum is a call to balance representation and reality, to honor both the maps that guide us and the world they depict. It challenges us to navigate not just geography, but our beliefs, our doubts, and our dreams. As you drift towards sleep, let this enigma be a gentle invitation, a chance to ponder the maps you follow and the stories they tell about your place in the cosmos. As we fold away the distorted maps, our minds swirling with questions about geography and the stories we tell about the world, let's turn to another flat Earth mystery. If the Earth is a flat plane, how do its oceans rise and fall in their timeless rhythm? What forces drive the tides in a world without a moon's gravitational pull? Let's explore a tidal mystery that ebbs and flows at the edge of imagination. Stand at the edge of the sea, where waves kiss the shore, and feel the rhythm of the ocean. It ebbs and flows, a ceaseless dance of water that rises and falls twice each day, as if breathing with a life of its own. The tide is a constant, a pulse that has shaped coastlines, guided sailors, and whispered secrets to those who listen. On a spherical Earth, this rhythm is explained by the moon's gravity, an invisible force that tugs the oceans toward it, creating tidal bulges that sweep across the globe. But what if the Earth is not a spinning globe orbiting the sun? What if it's a flat plane, stretching out beneath a dome or an open sky? How, then, do the tides rise and fall? What force drives the ocean's dance in a world where the moon is not a distant satellite, but a local light or projection? In flat Earth cosmology, this is the tidal flow enigma, a mystery that stretches the imagination and challenges our understanding of the natural world. The idea of tides without the moon's gravitational pull is both poetic and perplexing. It reimagines the ocean's rhythm as the result of unseen forces, perhaps electromagnetic fields, the motion of the flat Earth itself, or mechanisms yet to be discovered. This vision evokes a world where the tides are a self-contained phenomenon, independent of the cosmos, yet raises questions that ripple through our understanding. Why do tides align with the moon's phases? Why do they vary so predictably across the planet? In this segment, we'll explore the tidal flow enigma, not to affirm or refute the flat Earth model, but to unravel its allure. We'll weave through the interplay of science and mystery, history and philosophy, to understand why this enigma captivates and what it reveals about our connection to the rhythms of the Earth. So, take a slow, deep breath, imagine the ocean's gentle surge, and let's dive into this mystery, an enigma that pulses with the heartbeat of the sea. Picture yourself as a fisherman in an ancient coastal village, watching the tide creep up the beach at dawn and recede by dusk. You notice it follows the moon, higher tides when the moon is full, gentler ones when it's a sliver. You weave stories of a lunar spirit pulling the waters, a tale that feels true in your bones. Now, imagine a flat Earth theorist standing on that same shore, claiming the tides are driven not by the moon, but by the Earth's own hidden forces. This reimagination taps into the same instinct that inspired your stories, the need to explain the ocean's rhythm, to find meaning in its ceaseless flow. As we explore this enigma, we'll ask, how does a flat Earth account for the tides? Why does this idea resonate? And what does it reveal about our bond with the sea and the sky? In flat Earth cosmology, the Earth is a flat, circular plane with the North Pole at its center, the continents radiating outward, and an ice wall, often identified as Antarctica, encircling the whole. The Moon, rather than a rocky satellite 384,000 kilometers away, is envisioned as a small, local object, perhaps a few miles across, circling above the plane at a height of a few thousand miles. In this model, the Moon cannot exert the gravitational pull needed to drive tides, as gravity itself is often reimagined or replaced by other forces, like buoyancy or electromagnetic effects. To explain the tides, flat Earth proponents propose alternative mechanisms. Some suggest the flat plane oscillates or tilts, causing the oceans to slosh like water in a pan. Others propose electromagnetic fields, generated by the Earth or the dome-like firmament, that periodically push or pull the seas. Still others attribute tides to the cyclical motion of the sun and moon, whose movements might create pressure waves or atmospheric effects that stir the waters. To visualize this, imagine the flat Earth as a wide, shallow bowl filled with water, representing the oceans. The bowl is stationary, but an unseen force, perhaps a gentle rocking motion or a magnetic pulse, causes the water to slosh, creating waves that rise and fall along the edges. This is the flat Earth tide, a localized phenomenon driven by internal or atmospheric forces, not a distant moon. The sun and moon, circling above, might amplify these waves, their light or energy interacting with the water in ways not fully explained. Flat Earth proponents argue that this model accounts for the tide's daily rhythm without needing a spherical Earth or gravitational forces, and they might claim that the correlation between tides and lunar phases is coincidental or due to the moon's cyclical path above the plane. In scientific terms, tides are driven primarily by the moon's gravitational pull, with a secondary contribution from the sun. The moon, orbiting Earth at an average distance of 384,000 kilometers, exerts a gravitational force that creates two tidal bulges on Earth's oceans, one on the side facing the moon, where the pull is strongest, and one on the opposite side, due to inertial effects. As Earth rotates every 24 hours, these bulges move across the planet, causing two high tides and two low tides daily at most coastal locations. The sun's gravity, though weaker due to its greater distance, 149.6 million kilometers, amplifies tides during full and new moons, spring tides, and dampens them during quarter moons, neap tides. This model explains why tides correlate with lunar phases, why they vary in amplitude based on coastal geography, and why precise tidal predictions are possible using gravitational equations and historical data. The flat Earth model, however, struggles to account for these observations. If tides are caused by the Earth's motion or electromagnetic fields, why do they align so closely with the moon's position in the sky? Tide tables, used by sailors for centuries, predict high tides when the moon is overhead or on the opposite side of Earth, a pattern consistent with gravitational forces, but difficult to explain with local oscillations or atmospheric effects. The flat Earth model also fails to explain why tides vary globally. For example, the Bay of Fundy in Canada experiences tides up to 16 meters, while some Pacific islands see tides of less than a meter, a variation tied to the spherical Earth's geometry and coastal shapes. If the flat plane oscillates uniformly, why aren't tides consistent across all shores? The scientific model, with its gravitational framework, accounts for these differences with precision, while the flat Earth model requires additional, untested mechanisms. Another challenge is the sun's role. In the scientific model, the sun's gravity contributes to tidal patterns, particularly during spring and neap tides, which align with the sun-moon-Earth geometry. In the flat Earth model, the sun is a local light, circling with the moon, yet its influence on tides is rarely detailed, leaving gaps in explaining why tidal cycles follow both lunar and solar rhythms. Historical tidal records, dating back to ancient China and medieval Europe, show consistent lunar correlations, supporting the gravitational model. Modern instruments, like tide gauges and satellite altimeters, map tidal heights globally, confirming the spherical Earth's tidal dynamics. Flat Earth proponents might dismiss satellite data as fabricated, but this doesn't explain ground-based measurements or the predictive power of gravitational theory. Let's explore this with an analogy. Imagine a bowl of water on a table, gently tilted back and forth, causing the water to slosh, creating waves that mimic tides. This is the flat Earth model, a local mechanical process driving the ocean's rhythm. Now, picture a spherical balloon filled with water, orbiting a lamp, the moon, whose gravitational pull stretches the water into bulges that shift as the balloon spins. This is the scientific model, a cosmic interaction between Earth and moon. The bowl analogy captures the flat Earth model's simplicity, but it can't explain why the sloshing aligns with the moon's cycle, why tides vary by location, or why the sun plays a role. The scientific model, while more complex, accounts for these phenomena with elegance, from coastal tides to global patterns. Historically, tides were a key to understanding gravitational forces. In the 17th century, Isaac Newton's theory of universal gravitation explained tides as the result of the moon's pull, building on earlier observations by Johannes Kepler and Galileo Galilei. By the 19th century, scientists like George Darwin, Charles Darwin's son, developed tidal dynamics, linking tides to Earth's rotation and lunar orbit. These discoveries reinforced the spherical Earth model, as tidal patterns matched a globe's geometry. Flat Earth theories, however, revive pre-Newtonian ideas, seeking alternative explanations that avoid gravity, often drawing on ancient myths where tides were the breath of gods or the Earth's own pulse. The tidal flow enigma, while evocative, struggles against the weight of historical and modern evidence, requiring speculative forces where science offers clarity. Flat Earth proponents argue that the scientific model relies on unprovable assumptions, like gravity or a distant moon, and that tides can be explained by local phenomena, like electromagnetic waves or the Earth's motion. They might claim that lunar correlations are overstated or that tidal data is manipulated to support a spherical Earth. Science counters with reproducibility. Tide gauges measure sea levels, satellites track ocean heights, and fishermen predict tides using lunar charts, all consistent with gravity. The tidal flow enigma, while poetic, bends under the scrutiny of global observations, where the moon's pull remains the simplest explanation. The tidal flow enigma is more than a debate about ocean mechanics. It's a profound challenge to our understanding of the unseen forces that shape our world. If the tides are not caused by the moon's gravity, What hidden mechanisms might be at play? This question ripples outward, inviting us to reconsider the cosmos and our place within it. The flat Earth model, with its local tides driven by unknown forces, offers a vision of a self-contained Earth, where the ocean's rhythm is intrinsic, not tied to a distant celestial body. It's a comforting image, suggesting a world that operates on its own terms, independent of a vast, impersonal universe. But it severs the bond between Earth and Moon, a connection that has inspired myths, poetry, and science for millennia. The tension between these perspectives, between a self-sufficient plane and a cosmic dance, raises questions about our relationship with nature, the rhythms we live by, and the forces we cannot see. Let's linger on the idea of unseen forces. Tides are a reminder that the world is shaped by powers beyond our senses: gravity, magnetism, the spin of the planet. In the flat Earth model, these forces are reimagined as local, perhaps electromagnetic or mechanical, suggesting a world where mysteries are closer, more tangible. This vision resonates with our instinct to seek explanations within reach, to feel that the Earth's rhythms are part of a design system. The scientific model, with its moon-driven tides, places these forces in a larger context, linking us to a cosmos where Earth is one body among many, influenced by distant stars and satellites. The Tidal Flow Enigma asks, do we prefer a world where forces are local and contained, or one where we're connected to the universe? This choice mirrors our personal searches for meaning, where we weigh the comfort of self-contained answers against the awe of cosmic connections. Philosophically, the enigma touches on causality and interconnectedness. The 18th century philosopher David Hume argued that we infer causes from observed effects, but our understanding is limited by experience. The flat Earth model infers tides from local causes, oscillations, fields, based on a flat plane's constraints, while the scientific model infers gravity from tidal patterns, lunar cycles, and global data. The tidal flow enigma challenges us to question our causal assumptions. Do we trust the moon's pull because it fits the evidence, or because it's the story we've been told? This resonates with modern debates about science and belief, where we navigate competing explanations in a world of information overload. The flat Earth model, with its alternative forces, invites skepticism, but also risks isolating us from the interconnected cosmos that science reveals. The enigma also raises existential questions about rhythm and connection. Tides are a heartbeat, a pulse that links humanity to the natural world. In myths, they're the ocean's breath, tied to lunar deities like the Greek Artemis or the Polynesian Hina. In science, they're a gravitational dance, connecting Earth to the moon and sun. The flat Earth model breaks this connection, suggesting tides are an earthbound phenomenon, not a cosmic one. This shift is both liberating and isolating. Liberating because it frees the Earth from external forces, isolating because it cuts us off from the sky. What does it mean to live in a world where the tides are ours alone? What does it mean to lose the moon as a partner in the ocean's dance? These questions echo our broader quest for connection, whether to nature, the cosmos, or each other, as we seek rhythms that ground us. Let's explore this through a historical lens. Tides have shaped human history, from ancient fishing villages to modern ports. In the Middle Ages, monks recorded tidal cycles, noting their lunar links, which informed navigation and trade. Newton's 1687 work, Mathematical Principles of Natural Philosophy, formalized tides as gravitational effects, cementing the spherical Earth model. The 20th century's satellite era refined tidal predictions, supporting coastal engineering and climate studies. The flat Earth model revives older visions, like those of ancient mariners who saw tides as earthly or divine, not celestial. The tidal flow enigma is a clash of paradigms, pitting modern precision against ancient intuition, asking whether we explain the ocean's pulse with equations or mysteries. Psychologically, the flat Earth model taps into our need for autonomy. By attributing tides to local forces, it suggests a world we can master, where the Earth's rhythms are ours to understand without cosmic intermediaries. The scientific model, with its distant moon and complex gravity, can evoke humility, reminding us that we're part of a larger system. The Tidal Flow Enigma asks, do we seek control over the forces that shape us, or do we embrace our place in a cosmic web? This tension mirrors our personal struggles, where we balance independence with interdependence, seeking to steer our lives while flowing with life's rhythms. Let's deepen this with a cultural perspective. Tides are a universal symbol, appearing in literature, art, and spirituality as metaphors for change, renewal, and mystery. In Shakespeare's The Tempest, the sea's ebb and flow reflect human fortunes, tied to unseen forces. The flat Earth model, with its local tides, aligns with this symbolic view, suggesting a world where rhythms are intimate, not cosmic. The scientific model, with its gravitational tides, expands this symbol, linking human experience to the universe. The Tidal Flow Enigma asks us to choose between a personal, earthly rhythm and a universal, celestial one, a choice that shapes how we tell stories about our world. Let's pause here, as the video's meditative tone invites reflection. Picture the ocean, its waves lapping at the shore, rising and falling with a quiet cadence. Feel its rhythm, its pulse that seems to echo your own breath. What does the tide whisper to you? Is it a voice from the earth, a secret of the sea, or a call from the moon, pulling you toward the cosmos? As you listen, perhaps in the stillness of your room, let this question settle, a gentle wave in your thoughts. The Tidal Flow Enigma is not just a mystery. It's a mirror, reflecting our need for rhythm, our trust in unseen forces, and our endless search for connection in a flowing world. The Tidal Flow Enigma is a call to balance the seen and unseen, to honor both the rhythms we feel and the forces we measure. It challenges us to navigate not just the oceans, but our beliefs, our doubts, and our dreams. As you drift towards sleep, let this enigma be a quiet invitation, a chance to ponder the tides that move you and the forces that guide your way. As we rest in the rhythm of the tides, our minds filled with questions about the ocean's dance and the forces that drive it, let's turn to the final flat Earth mystery. In an age of science and discovery, why do these theories persist, captivating hearts and minds? Let's explore the psychology behind this enduring enigma, a question that pulls us to the heart of belief itself. Lie back and gaze at the night sky, where stars twinkle in a vast, quiet expanse. In our modern world, we navigate with GPS, marvel at images from space telescopes, and track satellites orbiting a spherical Earth. Science has mapped the cosmos with breathtaking precision, revealing a planet that spins on its axis, orbits the sun, and floats in a universe 13.8 billion years old. Yet, amidst this wealth of knowledge, some still believe the Earth is flat, a plane with a central North Pole, encircled by an ice wall, covered by a dome or open sky. Why, in an era of such clarity, do flat Earth theories endure? Why do they captivate hearts and minds, defying the evidence that surrounds us? The persistence of flat Earth beliefs is not just a question of science. It's a window into the human soul, a mystery woven from psychology, trust, and the search for meaning. This final segment invites us to explore not the flat Earth itself, but the reasons it lingers. These theories are more than cosmological claims. They're stories that resonate with our deepest instincts, to question authority, to seek simplicity, to find purpose in a complex world. They thrive in the shadows of doubt, where skepticism meets the need for a narrative that feels true. In this closing chapter, we'll unravel the persistence of flat Earth beliefs, not to judge or dismiss them, but to understand their allure. We'll journey through the interplay of mind and society, history and emotion, to ask why these ideas endure and what they reveal about us all. So, take a slow, deep breath, let the stars above guide your thoughts, and let's step into this final mystery, a quiet exploration of why flat Earth mysteries refuse to fade. Picture yourself as a seeker in a distant time, standing beneath the same stars, wondering about the world's shape. The elders tell you it's a flat plane, held by gods, or resting on an endless sea. Then, a traveler arrives, speaking of a spherical Earth, spinning through space. You hesitate, torn between the familiar and the new. Now imagine a modern soul, scrolling through online forums, finding flat Earth videos that challenge the globe they've been taught. The hesitation is the same, a pull between trust and doubt, comfort and curiosity. As we close this journey, we'll ask, why do some choose the flat plane over the globe? What drives the persistence of belief, and what does it teach us about our own convictions? Flat Earth beliefs persist in the 21st century despite overwhelming scientific evidence, because they tap into powerful psychological, sociological, and cultural currents. At their core, these beliefs are rooted in skepticism of institutions, governments, space agencies, academia, that promote this spherical Earth model. Many flat Earth proponents view these institutions as complicit in a grand deception, hiding the Earth's true shape to maintain control or obscure cosmic truths. This distrust is amplified by historical events, like government cover-ups or scientific errors, which fuel the idea that official narratives can be flawed. Psychologically, flat Earth theories offer a sense of control and simplicity in a world that feels increasingly complex. The idea of a flat, contained Earth with a central North Pole and a tangible boundary is intuitive, rejecting abstract concepts like gravity, heliocentrism, or a universe spanning 93 billion light-years. Instead, it proposes a cosmos that aligns with everyday observation. The ground feels flat, the sun appears to circle above, and the stars seem fixed in a dome. Sociologically, flat Earth beliefs thrive in online communities, where platforms like YouTube, Reddit, and X create echo chambers that reinforce alternative narratives. These communities provide a sense of belonging, where individuals who feel alienated by mainstream science or society can connect with like-minded skeptics. Videos, memes, and forums amplify flat Earth arguments. Claims about inconsistent moon landing photos, distorted maps, or the absence of visible curvature, creating a self-sustaining cycle of confirmation bias. The Internet's democratization of information allows anyone to challenge established truths, but it also blurs the line between evidence and opinion, making flat Earth ideas accessible and persuasive to those seeking answers outside the mainstream. To understand this, let's use an analogy. Imagine a comforting bedtime story told to you as a child, explaining the world in simple, familiar terms: a flat land under a starry roof, watched by a caring sun. As you grow, you learn a new story, a spherical Earth spinning through a vast, indifferent universe. The first story, though less accurate, feels warmer, more human. Flat Earth beliefs are like that childhood tale, offering a narrative that soothes by simplifying the cosmos and empowering the believer to reject a complex, institutional story. Now, contrast this with the scientific narrative, a detailed, evidence-based account, like a textbook, backed by data, but lacking the emotional warmth of the simpler tale. The bedtime story analogy captures the emotional resonance of flat Earth beliefs, but it falters against the textbook's rigor, satellite imagery, GPS, lunar rocks, that confirms a spherical Earth. Scientifically, flat Earth theories are debunked by countless observations. Satellite images show Earth's curvature, GPS relies on orbiting satellites, and Apollo missions left artifacts on the Moon, verifiable by laser ranging. Telescopes reveal planets as spheres orbiting the Sun, consistent with a heliocentric model. The Coriolis effect, driven by Earth's rotation, shapes weather patterns, and tidal cycles align with the Moon's gravity. These facts, reproducible across nations and disciplines, form a robust web of evidence that flat Earth models struggle to counter. Proponents often dismiss this evidence as fabricated, citing conspiracies involving NASA, the United Nations, or global elites. However, such conspiracies would require unprecedented coordination, thousands of scientists, engineers, and governments maintaining a lie for centuries. Without leaks, a scenario far less plausible than the scientific model's consistency. Historically, paradigm shifts have always faced resistance. In the 3rd century BCE, Aristarchus proposed a heliocentric model, but Ptolemy's geocentric model, with Earth at the center, dominated for 1,400 years, aligning with observation and theology. Copernicus's 1543 heliocentric theory, refined by Galileo and Kepler, met fierce opposition as it challenged the Church and common sense. The shift to a spherical Earth, confirmed by explorers like Magellan and scientists like Newton, was gradual, resisted by those who clung to flat or geocentric cosmologies. Flat Earth beliefs echo this resistance, reviving pre-modern ideas in a modern context, where distrust in authority amplifies their appeal. They're a modern echo of the struggle between intuition and evidence, between a world that feels true and one that measures true. Psychologically, flat Earth beliefs address cognitive and emotional needs. The concept of cognitive dissonance, the discomfort of holding conflicting beliefs, explains why some reject complex scientific models for simpler ones. A flat Earth avoids the dissonance of abstract concepts like gravity or a 13.8 billion-year-old universe, offering a model that matches sensory experience. The horizon looks flat, the ground feels still. The need for agency also plays a role. Believing in a flat Earth empowers individuals, positioning them as truth seekers against a deceptive system. This aligns with the Dunning-Kruger effect, where limited knowledge can lead to overconfidence, as some dismiss expert consensus without fully understanding it. Emotionally, flat Earth beliefs provide a sense of purpose, suggesting a designed world where humanity is central, not a speck in an indifferent cosmos. Sociologically, the rise of flat Earth beliefs reflects broader cultural trends. The internet has decentralized knowledge, allowing alternative voices to challenge mainstream narratives. This democratization is empowering but risky, as misinformation spreads alongside insight. Flat Earth communities, often found on platforms like X, foster a sense of identity, where members share experiments, like observing the horizon, to prove a flat Earth. These communities mimic scientific methods, but lack rigor, prioritizing narrative over data. The post-truth era, where feelings can outweigh facts, amplifies this, as flat Earth beliefs resonate with those who feel marginalized or distrustful of elites. The scientific community, while rigorous, can seem aloof, failing to engage emotionally with skeptics, which leaves room for alternative narratives to flourish. Let's deepen this with another analogy. Imagine a village where everyone trusts a single map, showing a spherical world. A stranger arrives with a different map, flat and centered, claiming the first is a lie. Some villagers, wary of the mapmaker's authority, embrace the new map, finding it simpler and more human. This is the Flat Earth movement, a rebellion against the dominant map, fueled by distrust and a desire for a world that feels accessible. The scientific map, backed by measurements, guides the world's journeys, but the flat map, though flawed, offers emotional clarity. The village analogy highlights the social dynamics of belief, but it can't explain why the scientific map enables GPS, flights, and space exploration, while the flat map falters under scrutiny. Flat Earth proponents argue that science relies on unprovable assumptions, like the existence of space or gravity, and that their model better matches observation. They point to cultural touchstones like distrust in NASA or the appeal of biblical cosmologies as evidence of a hidden truth. Science counters with transparency. Data from satellites, tide gauges, and telescopes is publicly accessible, and experiments, like measuring Earth's shadow on the moon during a lunar eclipse, confirm a globe. The persistence of flat Earth beliefs, while scientifically untenable, thrives on emotional and social resonance, offering a narrative that feels empowering in a world of uncertainty. The persistence of flat Earth beliefs is more than a curiosity. It's a mirror reflecting our own convictions, doubts, and desires. Why do we believe what we believe? This question, sparked by the Flat Earth movement, challenges us to examine the foundations of our knowledge, the communities we trust, and the stories we hold dear. The Flat Earth model, with its flat plane and cosmic dome, offers a world that feels certain, centered, and purposeful, a stark contrast to the scientific universe, vast and indifferent, where Earth is a fleeting speck. This contrast raises existential questions about truth, belonging, and the human need for certainty, inviting us to explore not just the shape of the Earth, but the shape of our inner worlds. Let's linger on the nature of belief. Flat Earth theories persist because they address universal needs: the need for control, for community, for a narrative that makes sense of a chaotic world. In a time of rapid change, globalization, technological leaps, cultural shifts, the simplicity of Flat Earth offers stability, a return to a world where the ground is steady and the sky is close. This resonates with the psychological concept of ontological security, the need for a consistent sense of reality. The scientific model, with its complex equations and cosmic scale, can disrupt this security, evoking existential anxiety about our place in an infinite universe. The Flat Earth model counters with a contained cosmos, where humanity is central and the world feels like home. The implication is profound. Our beliefs are not just about facts. They're about how we cope with uncertainty, how we find meaning in a world that often feels overwhelming. This leads to questions of trust and authority. Flat Earth beliefs thrive on skepticism of institutions, a sentiment rooted in real grievances, government secrecy, corporate greed, scientific errors. When trust erodes, alternative narratives fill the gap, offering a sense of empowerment. Believing in a flat Earth is an act of rebellion, a declaration that one's intuition trumps the expert's data. But this rebellion comes at a cost. It isolates believers from the collective knowledge that enables modern life, from GPS to climate models. The scientific community, while rigorous, often struggles to bridge this gap, presenting data without addressing the emotional needs that drive skepticism. The persistence of flat Earth beliefs challenges us to ask, how do we rebuild trust in a fractured world? How do we balance skepticism with openness, ensuring that questioning authority doesn't lead to rejecting evidence? Philosophically, the Flat Earth movement touches on epistemology, the study of knowledge and belief. The 17th century philosopher René Descartes sought certainty by doubting everything, building knowledge from first principles. Flat Earth proponents follow a similar path, doubting scientific claims and relying on personal observation. The horizon looks flat, so the Earth must be. This radical skepticism, while empowering, ignores the cumulative nature of science, where observations, like satellite imagery or tidal cycles, build a coherent picture. The scientific method, with its peer review and reproducibility, offers a path to certainty, but requires trust in a process that can feel distant. The Flat Earth model, by contrast, offers immediate certainty, aligning with sensory experience, but faltering under scrutiny. The implication is a challenge. How do we know what we know? And what do we do when intuition clashes with evidence? The sociological implications are equally compelling. Flat Earth communities, often online, create spaces where individuals find validation and belonging. These echo chambers reinforce beliefs, as members share experiments, like laser tests over water, to prove a flat Earth. This mirrors the dynamics of religious or ideological groups, where shared narratives foster identity. The scientific community, while collaborative, can seem exclusive, its jargon and gatekeeping alienating outsiders. The persistence of flat Earth beliefs highlights the power of community in shaping belief, suggesting that science must engage not just with facts, but with the human need for connection. What does it mean to belong to a truth? How do we build communities that value evidence without dismissing doubt? Let's explore this through a historical lens. Resistance to new ideas is timeless. When Copernicus proposed a heliocentric universe, he faced ridicule. Galileo was imprisoned for defending it. The shift to a spherical Earth, confirmed by circumnavigations and telescopes, took centuries as people clung to geocentric or flat models that felt intuitive. The flat Earth movement is a modern parallel, resisting a scientific paradigm that, while robust, can feel impersonal. This resistance reflects a broader human tendency. We hold on to beliefs that anchor us, even when evidence points elsewhere. The implication is humbling. Our convictions, whether scientific or alternative, are shaped by the same human instincts, the same need for a story that holds. The existential implications are perhaps the most profound. Flat Earth beliefs offer a world with purpose, where the Earth is a stage and humanity is the star. The scientific universe, vast and ancient, can evoke awe but also insignificance, a sense that our lives are fleeting in cosmic time. The flat Earth model counters this with a narrative of design, where the flat plane and dome suggest a created world, often tied to spiritual or biblical cosmologies. This resonates with the human quest for meaning, a quest that science, focused on how rather than why, often leaves unanswered. The persistence of flat Earth beliefs asks, what stories give us purpose? What beliefs make us feel at home in the cosmos? These questions invite us to reflect on our own anchors, the truths we hold to navigate life's uncertainties. Let's deepen this with a cultural perspective. Flat Earth beliefs draw on archetypes of rebellion and revelation, found in myths where heroes uncover hidden truths. They align with countercultural movements, from 19th-century flat Earth societies to modern conspiracy theories, where questioning the mainstream is a badge of honor. The scientific narrative, while dominant, can feel like a monolith, its authority stifling to those who crave agency. The Flat Earth movement, with its DIY experiments and online manifestos, offers a cultural alternative, a space where skepticism is celebrated. The implication is a call to bridge this divide, to make science a story of shared discovery, not institutional decree. Let's pause here, as the video's meditative tone invites reflection. Picture yourself under the stars, their light ancient and steady. What beliefs anchor you in this moment? Are they truths you've tested, stories you've inherited, or doubts you're still exploring? What might you question if you stood beneath a different sky? As you listen, perhaps in the quiet of your room, let these questions settle, a gentle constellation in your thoughts. The persistence of flat Earth beliefs is not just a mystery. It's a mirror, reflecting our need for certainty, our hunger for community, and our endless search for meaning under the stars. The persistence of flat Earth beliefs is a reminder that belief is human, shaped by emotion, culture, and experience as much as by evidence. It challenges us to examine our own convictions, to balance doubt with trust, to find truth without losing wonder. As you drift towards sleep, let this final enigma be a soft invitation, a chance to ponder the beliefs that guide you and the stars that light your way. This is our final segment, but the mysteries of the flat Earth linger. As you drift towards sleep, let these ideas swirl gently in your mind, like stars in a quiet sky. The questions we've explored about trust, truth, and the shape of our world need no answers tonight. Let them be a lullaby, a whisper of wonder, carrying you into dreams where the Earth is whatever you imagine it to be.